Okay, do you want to exit?
Yeah, just exit and then do the slideshow again.
So yes, welcome everyone to the Zero Knowledge Proof workshop. Great. Yes, thanks everyone for being here. So the workshop actually is really popular. There will be more people coming, and then we actually have an overflow room if this room doesn't have enough capacity. Okay, so first, this workshop is hosted by the new campus-wide center at Berkeley in blockchain Web3 called the Berkeley Center on Responsible Decentralized Intelligence. And so the center is a campus-wide multidisciplinary center covering across campus from different schools, including engineering school, the Haas Business School, and the law school, and so on. And are working together with the faculty and students in the center to advance towards a mission for advanced science and technology of Web3, decentralization, decentralized intelligence, to make it universally accessible and empowering a responsible digital economy. And for more information, you can go to the RDI website. And also, so the RDI website is quite unique in the sense that it has three key pillars for this RDI Innovation Center, including research. So you can, again, learn more research about the center on the center website. And also at today's workshop, you actually will learn a number of projects coming out of the center as well. And the second pillar is education. And then the third one is community and entrepreneurship. So for education, the Berkeley Center has been collaborating with other universities and institutions, developing MOOCs, massive open online courses. So a number of you may have seen the world's first decentralized finance MOOC, the DeFi MOOC, and also recently we announced a second MOOC on entrepreneurship in Web3. And again, you can learn more information by going to the MOOC's website. So following the the efforts of developing MOOCs to help the community to gain more knowledge and experience in Web3 and blockchain. So today we are going to announce, we have a new announcement that together with a number of speakers here, including Dan and Shafi will be here in the afternoon, and Yupeng and Justin Taylor, we are launching a new MOOC on Zero Knowledge Proof. This will start in spring 2023. And you can find out more information, and also you can sign up on zk-learning.org. And also it would be great if you can help spread the word by retweeting my tweet about the MOOC. With that, since this is a ZKP workshop, there is no better place to announce the new MOOC. So thanks, everyone, and hope to see many people in the MOOC as well. And now, just very briefly, in terms of logistics for the workshop, So we have a really exciting agenda for the workshop with many really amazing researchers as speakers in this workshop. So please find out more information on the workshop website for the schedule. And also, to make it easy to make announcements, you are welcome to join the RDI Telegram channel so that we can use the channel to make any announcements as needed for the workshop. And also, besides the invited talks, we also have a number of faculty, students, researchers giving contributed talks. And given that we have many talks, so each one can, for this contributed talk can only be 5 minutes, and we'll do the Q&A at the end. And also, finally, at the end of the workshop, we have a reception here. And after the reception, we also welcome everyone to join the workshop dinner, co-hosted by a number of entities at downtown Berkeley. So with that, thanks, everyone. One more, sorry. One more slide. So I also wanted to mention that this ZKP workshop is an affiliated event with the CESC, which actually starts on Monday. We'll be on Berkeley campus Monday and Tuesday. So CESC has received more than 170 papers in submission. So it's the conference with the highest number of paper submissions in blockchain Web3 to date, and also has so far registrations over 2,500. And with CESC, also there are affiliated events, including the Berkeley Blockchain Accelerator Demo Day on Tuesday. So as I mentioned, the RDI has a third pillar, which is entrepreneurship. And the Berkeley Blockchain Accelerator is actually the third pillar of the Center RDI. So we look forward and welcome everyone to join CESC, and in particular, also including the demo day. And also on Monday evening, there is a career fair for people who are interested in learning job opportunities in blockchain Web3 as well. Thank you.
Okay. Hi, everyone. I'm Yupeng Zhang from Texas A&M. And so I'll give the first talk here. So it's really great to see so many people that are interested in zero-knowledge proof. And as you can see, we have such a great list of speakers and talks today. So the purpose of my talk is actually to set the stage for everyone by providing some background knowledge on the definitions, applications, also the constructions of zero-knowledge proof, especially for those who are not super familiar with this area. So I will mostly focus on some recent constructions of efficient zero-knowledge proof schemes. Let's start. So first, what is a zero-knowledge proof? A zero-knowledge proof is a cryptographic primitive that can ensure the integrity of computations while still preserving the confidentiality of secret data. So in a zero-knowledge proof, there is a prover and a verifier, and the prover has a piece of secret data, and we call it the witness. So using zero-knowledge proof, the prover can convince the verifier about a statement or property of this secret data. For example, he can say that a public computation C executed on this witness gives you this output. And the verifier is able to verify the correctness of this statement. And there are several important properties of zero-knowledge proof. So first one is easy, correctness. It means that if everyone's honest, then the verification always passes. The second one is soundness. So in this case, if the prover is malicious, he can do whatever he wants, but the probability of cheating, like returning a wrong output while still passing the verification, is extremely small in practice. Third, we have zero knowledge. So this time, if the verifier is in turn malicious, then the proof leaks no information about the prover's sensitive data. And finally, for some schemes that we are interested in, we also want succinctness, meaning that we want the proof size to be significantly smaller than the size of the computation and the witness, and also the verifier to be faster than computing the result. So with these properties, we have a zero-knowledge proof scheme. So zero-knowledge proof scheme was originally proposed in the seminal paper by Shafi Goldwasser, Sylvan Mikhaili, and Charles Rakoff in 1985. And since then, it has led to many important results in theoretical computer science, including in the area of interactive proofs, probabilistically checkable proofs, and so on. And in the early days, we also have zero-knowledge proof constructions for any language in NP in this paper by Joe Killen and this paper by Silvo Micali. And I believe Abhishek will give more details about the recent theoretical advancements of zero-knowledge proof in his talk later. So in recent years, zero-knowledge proof has found many great applications in various applications. So I guess the most popular one is in the domain of blockchain and cryptocurrencies. So cryptocurrency is a way to build so-called decentralized currency system by posting the transactions on this data structure of a blockchain like this. So the total market cap of all cryptocurrencies already exceeds $1 trillion. And the underlying technology of blockchain itself is interesting, leading to many new applications such as decentralized finance, NFTs, and more recently Web3. However, there are still many challenges in this area, including the privacy and scalability issues of blockchain cryptocurrencies. So in public blockchains, everyone can join leave, so there's no mutual trust among the users. So that's why everyone can just access the data posted on the blockchain, and there's no way to protect the confidentiality and privacy of users and data. And to give an example for the second issue of scalability, Bitcoin can handle about 5 to 7 transactions for all users around the world. While if you take a look at the centralized transaction system like Visa cards, it's dealing with 65,000 transactions per second. So there's a big gap in terms of scalability. So turns out we can actually use zero-knowledge proof to address both issues by posting a proof about the validity of these transactions. So because of the soundness property of zero-knowledge proof, by verifying these proofs, we can still make sure that the transactions are valid. And in this way to reach a so-called distributed consensus among all the users and miners. But at the same time, because of the zero-knowledge property of zero-knowledge proof, we can actually hide the sensitive information of these transactions, like the sender, receiver, and the amount of money. And in this way, we can build privacy-preserving cryptocurrencies. And in some other applications, such as ZK Rollup and ZK EVM, we rely on the succinctness of these proofs. So in these applications, we can batch thousands of transactions into one small, short zero-knowledge proof. And in this way, we can support many more transactions per block and to improve the scalability and reduce the cost of the transactions. So because of these nice technologies, right now, zero-knowledge proof is basically one of the most important technique in this domain. And we have a great list of talks today talking about the developments and applications, and I'm also eager to learn more about the new advancements in companies and industry. So beyond blockchains, there are also other applications of zero-knowledge proof, mainly driven by some of the research papers. So we have there are some papers on zero-knowledge proof for machine learning inferences, program analysis, and bug bounties. And in this year's Usenix, there was a paper about zero-knowledge proof, zero-knowledge middle box, trying to examine the internet traffic. And in the early days, there are also papers applying zero-knowledge proof for verifiable ASICs. Because of these cool applications, so in the past several years, there was a blowout growth of the number of papers on zero-knowledge proof. And here I'm just listing a small subset of these papers, focusing mainly on those with implemented systems. And as you can see, zero-knowledge proof can be based on various different cryptographic techniques, including pairing, discrete log, interactive proofs, and so forth. Basically every month there's a new zero-knowledge proof scheme paper posted online now. So it's really a great research area. And today, because of time limit, I'm mainly going to focus on those with succinct non-interactive proofs. So in zero-knowledge proof, we care about the following efficiency measures. So we have prover time, which is the overhead for this prover to generate this proof. And we also have clearly proof size and verifier time. Memory, yes, good one. But in addition to those, for some schemes to work, there are also another party involved called the preprocessor. So the preprocessor has to generate a secret key and derive certain public parameters in order for the prover and the verifier to run the protocol. And more importantly, this party has to delete the secret key completely after the generation. Otherwise, the security of these schemes won't hold. So this is called the trusted setup and is not desirable in some of the applications. So we also have another kind of measurement in terms of whether you have trusted setup or not in the schemes. So then in the rest of my talk, I want to give an overview and highlight some of the key ideas in many of these zero-knowledge proof constructions. So what I'm going to do is I'm going to pick one representative examples from each of these category and highlight the design protocols of these schemes and also present the kind of the advantages, disadvantages in terms of performance using this type of radar chart. With prover efficiency, proof succinctness, verifier efficiency, and also whether you have a transparent setup or not. So, okay, so then let's start with the QAP-based snark. In particular, it was originated from the paper called Pinocchio. So, so in order to build a scheme that works for arbitrary computations, a common technique in cryptography is to model the computation as a circuit. So as you may know, circuits are universal. So if you have a scheme that works for any circuit, then in principle, you can have a scheme that works for any computations that can be computed by a computer. So here I'm showing an example of an arithmetic circuit with addition gates and multiplication gates. And the prover's job now is to convince the public, convince the verifier that the evaluation of the circuit is correctly done on the prover's secret input and gives you some output. So first, the prover is going to evaluate the circuit. And let's label the wires, the values on the wires of this circuit using W1, W2, and all the way to Wn. So there are n wires in the circuit, and we view it as a vector like this. Okay? So in order to prove to the verifier that the evaluation of the circuit is correct, we are going to define some selector polynomials using this circuit. So for example, we can define a polynomial, Lix, such that Lij equals to 1 if the number Wi is the left input of a gate number j, a multiplication j. So for example, we have a multiplication gate here. Then we define L11 equals to 1, and L12 equals to 0, and everything else equals to 0. So in this way, we can find a unique polynomial with such a property. And this is called the selector polynomial. So similarly, we are going to define polynomial Rix and Oix using the right input and the output of a gate. So for example, here we want R21 equals to 1 and O91 equals to 1, assuming that this wire is W9. Okay. So the purpose of defining polynomials like this is that we can actually construct a master polynomial P of x like this. So it looks quite complicated, but I'm going to walk through it with an example. So you can see that this one is basically consisting of 3 pairs of parentheses with a big sum inside each parenthesis. So let's see what's the purpose of each summation. So we can actually evaluate this polynomial at a point, for example, P1. So what is P1 here? So if you substitute P1 into the first parenthesis, you can basically, by the definition of this Lix polynomial, you're asking who is the left input of gate number 1. Right? Then by the definition, W1 is the left input of this gate. So L11 equals to 1. So there's a term L11 times Wi, which is W1. For all other terms in this summation, they're all equal to 0 because they're not left input of this gate. So it turns out if you simplify this equation, this entire summation becomes a single value, that is W1. Okay? So that's actually much easier to deal with if you evaluate it. Similarly, if you take a look at the second summation, it equals to W2 because W2 is the right input of this gate. And then you have minus W9. So then what is W2 times W1 times W2 minus W9? Well, it should equal to 0 if your evaluation is correct because you're dealing with the multiplication gate. W1 times W2 equals to W1. So that's it. So because of this reason, this polynomial evaluates to 0 at point 1. So that's basically the magic of this design. So similarly, you can evaluate this polynomial at 1, 2, 3, 4, all the way to m, where m is the number of gates in your circuit. then you're basically iterating through all the gates and check that the evaluation of each gate is correct. So in this way, we transform the problem of circuit evaluation to the problem of this master polynomial being 0 at all of these points. And this is actually the kind of the classical design of quadratic arithmetic program proposed in these two seminal papers. So now the question becomes, how can we prove that this polynomial equal to 0 at these points? Then another common trick used in many of these zero-knowledge proof schemes is to prove that it has a factor of so-called vanishing polynomial. So this polynomial is x1 times x minus 1 times x minus 2 all the way to x minus n. And this polynomial equals 0 at all these points. So if this master polynomial p of x can be represented as a product of vx times hx, then it becomes 0 at all of these points. So these two are actually equivalent conditions. So finally, the last step is how can we compile this nice polynomial system into a zero-knowledge proof scheme. So right now, the prover wants to convince the verifier that this master polynomial is 0 at all these points, or can be represented as vx times hx. But he can't just send this entire polynomial to the verifier. That is too big. It's even bigger than the circuit and leaks all the information about the values. So the last step is use the technique of cryptography to compile it into a zero-knowledge proof. So in the setup phase, this trusted party picks a random secret key S and generates a set of public key where each public key is g to the power of the polynomial LIX evaluated at this secret point S. And this is the trusted setup step I was talking about. And with the help of these public parameters, then the prover can generate this constant size proof without sending this entire polynomial to the verifier. So each proof, for example, pi1, is just the g to the power of this polynomial defined by this summation, evaluated at the secret point S. And the result is a single value. Okay? And that's why the proof size is constant. And similarly, the prover is going to compute pi2 using the second summation, pi3 using the third summation, and finally, pi4 equals to g to the power of hs. And the verifier can verify this equation, the relationship of this equation, using so-called bilinear pairing. So using the pairing, the verifier can check that the equation holds on the exponent of this group. So that is basically the key idea of this design to compile it into a zero-knowledge proof. And the real protocol, of course, is much more complicated than this, so I'm not going to mention the details of that one. So yeah, so that's the construction of the QAP-based snark. So one more note on the computation supported by this type of snark. So you probably heard a common word called R1CS. What is that? So that is actually called rank 1 constraint system. So before I define this problem using a circuit, right, there's a vector of circuit evaluation, and then we have these selector polynomials to select one element from this vector. But then who says that we have to use either 1 or 0 to select it? And we can actually make it to be any public constant. Then we get this new system called rank 1 constraint. So basically you're selecting from a subset of variables from this entire vector, multiply them with some constant that are publicly known, and then put them into one of these pair of parentheses in this equation. So you have a summation times another summation minus another summation equal to 0. So that is R1CS we are talking about. And that's a generalization of arithmetic circuits. So to see the performance of snark, I guess the most important advantage of snark is it has the smallest proof size. So we're talking about a little bit more than 100 bytes, depending on which curve you're using to do the bilinear pairing. And the verifier time is also super fast. Okay, so you can see that in this radar chart, you have great proof succinctness and great verifier efficiency. But the drawback of this scheme is the prover time is relatively slow because it's using this fast Fourier transform and also modular exponentiations. And also it requires a per circuit trusted setup because we need to generate these public parameters using the circuit. You have to do it again for every other circuit. So that is why it may not be great for applications like proving smart contracts with different functions. And the front end is R1CS, and we also have these great related schemes dated back to Pinocchio. We have libsnark, Geppetto, Gross16, which is more commonly used in practice because of the smallest proof size. So this is the grid line of work that is a QAP-based snark. So then, as you can see, the issue of this snark, one of the issues of this QAP-based snark is this per circuit trusted setup. So motivated by this, there are schemes trying to improve this aspect a little bit by proposing schemes that has a universal trusted setup. You only need to do it once for all computations you want to support. And also, they still want to keep this constant size proof. And these schemes include Sonic, Planck, and Martin, and so forth. So I'm going to use Planck as an example to kind of highlight the key idea behind the constructions. Okay? So that is the second category of snark I'm talking about in this talk. So Planck, proposed by this paper, is also treating this computation as a circuit on the prover side. So our job is, again, to prove the correct evaluation of this circuit. But the way to encode these variables in the circuit is a little bit different from the QAP-based snark. So this time, we are going to have 3 vectors instead of 1. So A, B, and C, where A is the left input of a gate, B is the right input of a gate, and C is the output of a gate. So for every gate, we have 3 numbers, like A1, B1, and C1. Then with this type of encoding, you can see that there are some actual redundancy in this in these vectors. For example, C1 is both the output of first gate and also the input of this gate. So there will be 2 values in these 3 vectors that are the same. Okay, so this encoding is slightly different from the one used in snark. So with this encoding, then we can actually check the evaluation of the circuit using some gate relationship. For example, the first one is multiplication gate. Then we have A1 times B1 equals to C1. Right? And for addition gate, we have A2 plus B2 equals to C2. So you can see with this new encoding, you only need to check the relationship column-wise. Right? You don't have to select something from the vector. So the equation holds per column of these 3 vectors. So in general, we can write these equations using this one. So this includes both addition and multiplication. Again, I'm not going to go into details this one, but to show you an example, if you want to encode a multiplication gate, you just set L1 to be 0, R1 equals to 0, M1 equals to 1, and O1 equals to -1. So this is the same as A1 times C1 equals to C1. Okay? And similarly, for addition, you can have 1, 1, 0, -1. That is same as A2 plus B2 equals to C2. So this is the way to encode both addition and multiplications, and we can also take care of some public constant constraints on certain gates and wires. So then if we define things in this way, we will have 4 more vectors. So we can also put L, R, M, and O as vectors like this. So there will be just values of 1, 0, or -1 in these vectors. And the difference is that these are publicly known information defined by the circuit, by the computation. And these are secret values known only by the prover. So they're evaluations of the circuit from the prover's witness. So now the prover's job is to convince the verifier that the prover knows these vectors satisfying the set of equations in this form. Okay? So that is the problem we are solving now. So how can we do that? Again, through polynomial representation. So this time, we are going to define polynomials in kind of the most natural way using polynomial interpolation. So we want to define polynomial AX such that AI equals to element AI in this vector A for all the locations, 1, 2, all the way to A. Okay? So this is a one-to-one mapping polynomial interpolation. Similarly, we define BX, CX, LX, and so forth from these vectors. Once we do that, there's another kind of master polynomial for the Planck system that looks like Lx times Ax plus Rx times Bx, and so on and so forth, that maps with this equation for all of these locations of the gates. Okay? And this master polynomial, again, has to be 0 at all points 1, 2, 3, 4, all the way to n, because of the equations on top like this. So they're equivalent with each other. So then how can we check that a polynomial equals to 0 at these points? Well, using our old friend, the vanishing polynomial. So this is the same technique as in snark. So we're going to check that p of x equals to vx times hx, where vx is the vanishing polynomial, like this. So in this way, we build another constraint system using polynomial with this new encoding proposed in the Planck system. So finally, how can we check this? Well, the tool used in Planck is slightly different from the QAP-based snark. So they're using a building block called polynomial commitments that were proposed in this paper by Akata et al. In Asia Crypt 2010. So in this building block, the prover can commit to a polynomial and later can allow the verifier to check a random point and then prove that this polynomial evaluated at this random point r equals to this number with the verification. So basically, this is a special purpose zero-knowledge proof for polynomial evaluation only. And we have a scheme in the original paper based on bilinear pairing. And I won't talk about details of this building block, but the most important thing is that there's only one-time trusted setup where the public parameters look like g to the power of different powers of this secret key s. Okay. So using this tool, we can actually build this zero-knowledge proof scheme called Planck. So the scheme works as follows. First, the prover commits to all of these polynomials defined by these vectors. Then the verifier checks the relationship at the random point. And eventually, the prover opens these polynomials at this random point and sends them to the verifier. The verifier verifies that they're consistent with these commitments and then check this polynomial equation at this random point. And by the famous Schwarzschild lemma, this guarantees that the polynomial equation holds with high probability, because in order to check a polynomial equality, it suffices to check it at the random point. And so that is the key idea behind the Planck system. So, and in the real protocol, there are also other checks, because you also need to ensure that there's some redundancy in these three vectors, where some of the values are the same. And this is called the permutation check in the paper. And I'm not going to talk about details of this part, but they can also be reduced to polynomial equality checks in a similar way. So finally, to show you the performance, so with this nice scheme, we can actually improve the trusted setup from per circuit to one time. It's universal for all computations. And the proof size is still constant. We're talking about like 400 to 500 bytes, so that's still pretty good. And the disadvantage is that it still requires FFT and exponentiations. So the prover time is kind of relatively slower in practice. Okay? And here I'm still listing this one as a disadvantage because there are other schemes without any trusted setup. But this is better than QAP-based snark. And here I also want to give credits to other schemes like Sonic and Marlin. So they were around the same time and also achieved the same universal and updatable trusted setup. But they're based on like completely different constraint systems and constructions. So yeah, so this one is for schemes with one-time trusted setup. So, well, the Planck scheme is actually used a lot in practice for a lot of applications. The performance is great, but they still require this one-time trusted setup, which may not be desirable for certain applications. So motivated by this, there are other schemes trying to completely remove the trusted setup. And here I'm just listing some of these schemes in the rest of my talk. First, we have this construction called Boole proofs that is based on the discrete log argument technique proposed by Budo et al. In this paper. And it still has a very small proof size. We're talking about 1 to 2 kilobytes for like big circuits, and does not have any trusted setup at all. Okay, so we call this one as a transparent setup. But the main kind of disadvantage of this system is that it always has a linear verifier time in the size of the circuit. So it may not be good for a delegation of the computations for a short, succinct verifier. And it supports front end of R1CS and has a particular good protocol for range proofs. So I believe Dan's going to talk more about this scheme in his talk, so I'm going to skip the details here, but just show this kind of a radar chart with the pros and cons. So another scheme that's trying, type of schemes trying to remove this trusted setup is based on this so-called doubly efficient interactive proofs that was proposed by Goldwasser, Klein, and Rothblum in this paper. And we refer to it as the GKR protocol. So the key idea of this GKR protocol is to view this circuit as a layered evaluation. So from the input as layer 0 and all the way to output as layer D. And the idea is to check the evaluation of the circuit layer by layer, instead of viewing it as a flat vector as in Planck and the QAP-based snark. So in order to do that, we are going to define a polynomial using the values in each layer of the circuit. And again, it's a polynomial interpolation. For example, the input is A0, A1, A2, A3, then we want V0 equals to A0, V1 equals to A1, and so on and so forth. So again, it's a one-to-one mapping. Okay? So similarly, we have one polynomial defined by each layer of the circuit, V1x, V2x, all the way to VDX. After that, we can see there's a relationship between two polynomials defined by two consecutive layers, simply because they're connected by the circuits. Right? For example, here we have a multiplication gate, then it means V10 equals to V00 times V01 by the definition of these polynomials. So in general, we can write this relationship as a function between VIX and VI minus 1x. And in the real protocol, we are actually using multivariate polynomials, but here I'm not going to differentiate them on the slides. Okay? So then based on this function, this relationship, the key idea of GKR protocol is to verify this evaluation, this relationship, layer by layer using the famous sum check protocol. So first, the prover is going to send the claimed output to the verifier, which is not trusted and is marked in red on slide. From this output, the verifier is going to derive this polynomial VDX and evaluate at the random point RD. Then the verifier is going to run an interactive protocol with the prover, and this is known as the sum check protocol. And at the end of this protocol, the verifier is going to receive a claim from the prover about this VD minus 1 are evaluated at RD minus 1. It's also not trusted, but the guarantee is that as long as this value is correct, so does VDRD and the output. So it's a reduction of the correctness to the previous layer. So after that, the verifier is just going to do it recursively with the prover, layer by layer, and reduce the correctness all the way to the input layer, and receive a claim about V0, R0. And here the guarantee is that as long as this V0, R0 is correct, so does everything else, including the output. So it's a reduction of the correctness to the input level. So that is the key idea behind the GKR protocol. So using this protocol as a building block and combining it with the polynomial commitment, several prior papers, including one of my earlier work, proposed a framework to build a zero-knowledge proof scheme. So the way it works is that the prover is going to define polynomial V0x using his secret data, the witness. Then the prover is going to run this interactive proof with the verifier to reduce the correctness of the output to this evaluation V0, R0. Then the prover is going to open this polynomial commitment at this evaluation point R0 and send the proof to the verifier. And this is the polynomial commitment part, as I explained before. Finally, the verifier is going to check the correctness of this evaluation that is consistent with the commitment, and then check that it is the same as the last message of the interactive proof, the GKR protocol. This completes the reduction of the GKR protocol and guarantees that everything, including the output, is correct. So in this way, we are able to build this zero-knowledge proof framework. And the main advantage of this line of work is that the prover efficiency is actually pretty good, especially for this interactive proof part. So the prover time in the original paper was kind of a polynomial time or cubic. But with the effort of the researchers in our community, we are able to bring it down to quasi-linear in this paper, and later with improvements for special circuits, and eventually it became a linear time, strictly linear in the size of the circuit in one of our earlier paper in crypto. So because of that, to kind of summarize the performance of this GKR-based schemes, it has great proof efficiency. There's no FFT or exponentials involved in the GKR part. Okay? But you may still need some of these operations in the polynomial commitment. And has a fast verifier time, and there's no trusted setup at all. But the main drawback of this line of work is the proof size is relatively large. We are talking about tens to hundreds of kilobytes, because the proof is literally linear in the depth of the circuit, and is also concretely large compared to other type of schemes. And the front end usually supports layer circuits, but we also have some work. There are also some schemes supporting R1CS. And here I'm listing the related work of Hyrax, ZKP, Seco, Libra, Virgo, Spartan, and so forth. And star means that in these schemes, it requires a one-time trusted setup. So this is the key idea behind this line of work based on GKR protocols. So the last category of the protocol I'll just briefly mention is this kind of well-known scheme called Stark. Okay? So I won't have time to go into details about the protocols, but I'll focus more on the kind of the representation of the computation. So the way Stark represents the computation is actually different from all the other schemes I mentioned before. They're not using circuits, but they work on the so-called arithmetic intermediate representation. Okay? So in this representation, we'll just have a table where so we have W variables in this table, and then T steps of this computation. And this computation is just going to update the values of these variables step by step. So it's more like the run-based computation, where you have a set of variables and you're updating the computation step by step. Okay? So this is the computation model used by Stark. So then from this kind of representation, we can define a computation using a certain constraints. So the constraints are represented using the polynomials, P1 all the way to PS, but the most important part is that it's a condition on the values in this table between every two steps of the computation. Okay? For example, you can think of you're going to do some additions between this one, and put the variable to this location. So that can be represented as a polynomial relationship between these two rows. Okay? So that's defined in this way. Okay? And that should equal to 0 for all the timestamps of this computation. And again, this computation is kind of universal, captures all computation, and that is used in Snark. So then I'll just very quickly go over the scheme. So the way to generate a proof for this type of computation is to view each column as a polynomial, like the entire history of one variable as one polynomial. Then we can actually encode all of these polynomials using these constraints defined by polynomial. And then the condition to check is that this polynomial equals 0 at all of these locations, 1, 2, 3, 4, all the way to t. Okay? Then how do you do that? And by this time, everyone should be familiar with this technique, right? Vanishing polynomial. Right? So to check that this is equal to 0 for all these locations, you factor it to be a product between the vanishing polynomial and another quotient polynomial. But the way they do it in the zero-knowledge proof scheme is different from the techniques before. They're not using any pairing-based groups. They're doing something called low-degree test. So they're going to compute this quotient polynomial, and the requirement is that this degree must be at most this one. Okay? So then this scheme is based on a kind of important work by the same set of authors earlier that year called Fry protocol. It's for low-degree test. So in this protocol, the prover can convince the verifier that a committed polynomial at most has degree D through certain interactions without sending the polynomial to the verifier immediately, directly. So the scheme is based on Merkle hash tree and the Reed-Solomon code. So again, I don't have time to go into details, but this one is actually known as the interactive arco proofs model. And this is actually a big breakthrough in this model for constructing zero-knowledge proof scheme. So using that protocol together with the constraint system I talked about before, they were able to build this Stark construction. And the advantages are fast prover time because there's no exponentiations involved, no trusted setup at all. But the drawback is that the proof size, again, tends to be relatively large. We're talking about tens to hundreds of kilobytes. And also at the same time, there are also other schemes like Ligero, Aurora, and Fractal, also based on this IOP model. And here I just want to highlight the names of these systems. So within this model, I also want to just say one word about this new line of research. So as you can see, all of these schemes either involve FFT or modular exponentiations. And the bottleneck of the poor time is indeed from these two major computations. So in order to further address these issues, recently there's a line of work using so-called linear time encodable error correcting code that then achieve strictly linear poor time for the entire zero-knowledge proof scheme. And the good thing is that there's no FFT or exponentiation involved. We are talking about linear number of additions and multiplications. But the drawback is that the proof size is really large because of the kind of distance of the code. So we're talking about megabytes or tens of megabytes. So, well, personally, I think this is a great kind of direction in the future to look into, and we also have some ongoing work to further improve the proof size. So to sum up, I guess the best way to kind of summarize my talk is through this radar charts again. So as I've talked about all these schemes, and so we have so many great constructions based on different cryptographic techniques, and we don't have like a winner of all yet. So they always have trade-offs on the proof efficiency, proof size, trusted setup, and so forth. So that is why I think that is a great area of research in zero-knowledge proof. And also, if you want to use it in applications for your products, then you can choose a proper one based on the properties you need for the application. So yeah, that's all for my talk. Thank you for listening.
Hi, thank you very much for this lovely talk.
There are some ongoing research and also papers from the community. So that's a great question. Yeah, thank you.
Great, yes. Thanks, Yipeng, for a great tutorial covering the recent developments in zero-knowledge proof systems. And I wanted to briefly mention, right, so this workshop is actually designed in such a way that, so in the morning, you'll get an overview with actually 3 key speakers from Yipeng, Dan, and Abhishek. You'll get an overview of the research, the huge body of research that has been done in zero-knowledge proofs, and also what people call the Campion explosion of ZKP systems in the recent years. And then in the afternoon, we'll go into more of, there's a lot of state-of-the-art actual frameworks that have been developed in industry and in general that actually helps people with real-world hands-on experience how to actually use these zero-knowledge proof systems. So with that, let's welcome Dan for the second talk on constructing modern snarks and also essentially giving some overview of the more advanced topics in zero-knowledge proofs. And Dan is, someone doesn't need an introduction. Okay, he's a professor of Stanford University, and okay, Dan will talk about it.
Great, thank you, Don. It's wonderful to see everybody here. I mean, this is a Sunday morning, so it's wonderful to see everybody interested in ZK proofs. So wonderful to be here, and yeah, let's see. So let's get started. So actually, when I was preparing this talk, I was kind of debating what to present, and I was thinking either I could go deep on one particular result, or I could kind of give a high-level survey of what's happening. But Yupeng actually gave a fantastic survey of the recent constructions. So that was a wonderful, wonderful survey. So I think what I'd like to do is basically generalize these constructions a little bit, and maybe kind of show you a different way of thinking of these families of constructions, kind of trying to put things into a single framework. And hopefully this will be helpful to you. And then if there's time, we'll get into more specific topics towards the end. I did want to mention this very large bibliography that was put together. It's kind of remarkable to see how much work is happening in the space. So if anybody's interested in kind of learning more about the techniques, please check out this bibliography. Okay, so let's get started. So I always start with this high-level intuition slide, which by now I don't think you need it, but we'll go through it anyhow. So a snark, of course, is a succinct proof that a certain statement is true. And the classic example is, I want to prove to you that I know a message M such that SHA-256 of M is equal to 0. And one would ask, well, what's wrong with the trivial proof, where the trivial proof is that I just send you the message M in the clear. And the problem, of course, with the trivial proof is that it's not succinct, right? The point of a snark is that we need a succinct proof. So if the message is a gigabyte long, sending you the message A is a very large proof, and B takes a long time for the verifier to verify. And we'd like both of these things to be, we'd like a short proof that is fast to verify. But I think this example already captures something that shows that this thing is like remarkable, right? I can prove to you that I have a pre-image of a hash function, a huge pre-image, with only like a 400 byte proof that only takes a constant time, or it's very, very, very fast to verify. Already, this looks incredible. This sounds like something that shouldn't be possible, and yet snarks make this possible. If you have to summarize to someone who has never seen this before, like how is this at all possible? It's kind of remarkable to me that if you unwind the entire stack that Yupeng just went through, the fundamental reason why this is possible is kind of remarkable. It's really because a univariate polynomial of degree d over a finite field can only have d roots. Yeah, this is fundamentally the reason that makes all of this work. It's kind of amazing that one simple fact enables this amazing thing. And of course, we can talk about ZK snarks, where the proof also reveals nothing about the message M. So we have these two notions of snarks. So the first thing I'd like to go through is just through some syntax and just define we agree on what a snark is, and then we'll go into more specific constructions. Okay, so what I'll define is what's called a pre-processing snark. Okay, so the first thing we have to define is what's called a nark. Let's ignore the succinctness property, and let's just focus on the non-interactive argument of knowledge property of these systems. And so let's define what's a pre-processing nark, so no S. And so we fix a certain circuit C. The circuit takes a statement and a witness. What we'll do is we'll first of all run through a setup procedure. So the setup procedure will pre-process the circuit. We'll see why we need to pre-process the circuit in a minute. It'll generate public parameters for the prover and public parameters for the verifier. Sometimes these are called prover key and verifier key. I actually prefer to use the term parameters rather than keys, because these things are not secret, right? Both of these parameters are public values that are available to the entire world to see. And so here the prover and the verifier would be given their corresponding parameters. The prover is given X and W, and of course the verifier is only given the statement X. What the prover will do is it will generate a short, succinct proof that in fact the circuit evaluates to 0 at the point X and W. And the verifier will choose to accept or reject. Yeah, so fundamentally this is kind of what we're trying to achieve. Let's go quickly through the syntax of what is a snark. So again, a nark, so a pre-processing nark, is made up of these three algorithms. The setup algorithm that does pre-processing, the prover, and the verifier. Yeah, so setup will output the parameters, the prover will output a proof, and the verifier will output accept or reject. Yeah, very simple syntax. There's one technical difficulty, which is that often we'd like to split the setup procedure, the pre-processing step, we'd like to split that into two separate algorithms. Yeah, so we call this a split setup, where S itself is made up of two algorithms. One is called the initialization algorithm, and the other is sometimes called the indexer. Yeah, so you notice that that S init takes no input. Well, it takes a security parameter as input and outputs these global parameters, and then the indexer is the one that actually takes the circuit and outputs the PP and VP. Yeah, the parameters for the prover and the verifier. Why do we split the setup into these two procedures? The reason is because we allow the initialization procedure to be randomized. And in particular, we allow it to use random bits. Yeah, so it needs to generate these random bits, generate GP, and then as Yupeng referred to, it has to forget those random bits. Yeah, if those random bits ever become public, we lose soundness of the system. Yeah, so we have to rely basically on this trusted step where the random bits are erased. But once we do this one-time initialization procedure, we can now process any circuit C in a deterministic way, and anyone can verify that the pre-processing was done correctly. So does that make sense? If we don't split it up into two halves, then we would have to run through a trusted setup for every circuit, and that was an issue with early SNARK systems. The modern SNARK system will do the split so that the initialization procedure only has to run once, and then we can pre-process any circuit deterministically. Yeah, so this allows us to do what's called a universal trusted setup. Okay, good. So that's what an ARC is. And then I guess I should say, for concreteness, we also allow all these algorithms in the adversary, we also allow them to have access to a random oracle. These SNARKs are typically set in the random oracle model, but I'm not gonna denote the random oracle in this in our syntax. Yeah, just keep in mind these algorithms have access to a random oracle. Okay, the requirements for an ARC are kind of, I guess Yupeng already went through them, so I'll run through them very quickly. So it has to be complete. It has to be what's called adaptive, it's to provide adaptive knowledge soundness. So adaptive knowledge soundness, the only, again, many of you know how to define this precisely, but the only subtlety that I'll point out is, right, so we need to have an extractor that can extract the witness from a successful prover. The only subtlety is which circuits are they attacking, right? So the prover is trying to convince the verifier that a certain circuit, that it knows a witness for a certain circuit, and the question is, who chooses the circuit and the statement X? In some papers, there's a universal quantifier saying for all circuits C, the extractor should work. That's a little problematic because it forces constructions to rely on non-uniform assumptions. So generally, the suggestion is to basically make it so that the prover is the one that chooses which circuit C to attack. And the reason we call this adaptive knowledge soundness is because the prover can choose which circuit to attack after seeing the parameters GP. Okay, so it's adaptive in its choice of circuit, and that makes, of course, proofs a little bit harder to do. Okay, so that's the knowledge soundness property, and of course we have the zero knowledge property that the proof should also reveal nothing about W. I'm not going to define that precisely. Okay, so that's what an ARC is. Hey, hope everybody is okay with this. Now let's add the S. Let's make it into a SNARK. So the S basically adds a succinctness property, which basically says that the proof itself needs to be short, so it can be the most logarithmic in the size of the circuit, and it should be fast to verify. Yeah, so succinctness means short and fast to verify. Again, the running time should be at most logarithmic in the size of the circuit. Of course, the verifier needs to read the statement X. Right, let's at least read the statement X, so we allow the running time of the verifier to be linear in the size of the statement, but it has to be logarithmic in the size of the circuit. And now you start to see why we need this pre-processing mechanism. Why do we need to pre-process? Well, the problem is if we allow the verifier to only run in logarithmic time in the size of the circuit, the poor verifier can't read the circuit. So it doesn't know what it's verifying, right? So if we had no pre-processing, the verifier simply can't read the circuit that it needs to verify. So really, what the pre-processing step is doing is, in some sense, it's summarizing the circuit for the verifier. This is kind of a remarkable thing where basically the pre-processing algorithm S, what it does is it outputs these verifier parameters VP that are very, very short so that the verifier actually has time to read VP. And this VP is a summary of this huge, huge circuit. It's kind of a summary that still allows the verifier to verify that the proof is correct. If you think about it again, this is kind of a remarkable thing that we can condense a huge circuit into a tiny string VP that lets you verify that the circuit evaluates to 0 at X and W. Yeah, that's the reason why pre-processing is necessary. Otherwise, we couldn't have a fast verifier. Okay, very good. At least for general circuits, we couldn't have a fast verifier. There are other types of computations that actually can have fast verifiers without setup, but let's not get into that. Okay, good. So that's the syntax for a snark. I hope everybody is okay with this. And so the next thing I want to do, well, okay, so snark actually I should say is basically complete, knowledge, sound, and succinct, and a ZK snark is a snark that also has a zero knowledge property. Good. So now let's switch gears and talk about constructing these snarks. All right. So what I want to tell you about is sort of this general paradigm that a lot of constructions fit into, and it's a very healthy way to think about these snark constructions. Yeah, so the paradigm basically combines two different components. Yeah, we combine what's called a functional commitment scheme with what we call an interactive oracle proof that's compatible with the functional commitment scheme. Yeah, so we combine these two things together, and out comes a snark. Yeah, and I want to walk through what these components are, and we'll see how the different constructions that Yupeng talked about actually fit into this paradigm. What's interesting is that the functional commitment scheme is where all the cryptographic dragons are hidden, right? All the hard complexity assumptions and crypto analysis goes into functional commitments, and then the IOPs themselves are nice, clean information theoretic objects that you can analyze just using algebra. You don't need any assumptions to actually argue that they're actually secure. All right, so what I want to do is basically walk through explaining each one of these concepts at a time, and then we'll see how the constructions fit into this paradigm. I should say that not all snark constructions kind of break down into these two steps. For example, the Gross 16 snark sort of melds it all into one monolithic construction, and it's not it doesn't split in this nice modular framework, but many of the modern snarks actually do fit into this framework. Okay, so let's get started. So I want to start with explaining the functional commitments part, and then we'll go into the IOPs. So let's see what is a functional commitment. So let's talk about what does it mean to commit to a function. This is something that was originally defined by Libera et al., but actually the specific version of committing to a function that we need is something that was defined in a paper with Wilson Ewan and Alex Ozdemir, and so I'll walk through that particular definition that we need. So the first thing we need to do is fix a family of functions. Okay, so remember this: the script f is a family of functions that we'd like to commit to. We'd like to commit to a member in this family of functions. So the prover basically has a function in the family set. And what we'd like to do is basically allow the prover to commit to this one member of the family. Yeah, so we're committing to a function in such a way that later the verifier can send a particular point in the domain, and the prover can prove that f of x is equal to y using one of these succinct proofs, as we'll see in just a second. Yeah, so what the prover commits to is an arbitrary function, and later it can prove that f of x is equal to y and that f is in the required family. By the way, this requirement here is extremely important. This is often when people talk about commitments and commitments to polynomials and such, they focus on the fact that f of x is equal to y, but it's actually really important to also prove that the function that we committed to is in the function family. For example, if we want to commit to polynomials of bounded degree, it's very important to also prove that not only is the polynomial evaluated correctly, it's also a polynomial of bounded degree. Yeah, otherwise, again, soundness doesn't work. Okay, so that's what a functional, so that's the syntax of committing to a function. Again, we can write down the syntax. Maybe I'll go through this very quickly. There's a setup to generate parameters. We can commit to the function using a commitment. It has to be a binding commitment. If we want zero knowledge, we might need to use a hiding commitment. And then there are these evaluation, there's an evaluation, either protocol or a pair of algorithms, P and V. P will let you produce a proof that f of x is equal to y relative to the committed function, and V will verify that proof. Now, what we want P and V to be is basically a snark for the relation saying that f of x is equal to y, f is in the required family, and in fact, the commitment to f relative to this random string r is the public commitment string. So the witness in this relation is the function f, or a description of the function f, and the randomness r. Okay? Now, here, it's actually very important. The K here is very important. It's very important that this be a proof of knowledge. In other words, when we prove that f of x is equal to y, it's important that we're able to extract the function from the prover, because that's going to be needed for the next step where we combine things with an IOP. Okay? So basically, again, a functional commitment is a snark or a ZK snark for this very simple relation for a particular family of functions. Okay. So far, so good. So now we understand what a functional commitment scheme is. Allows us to commit to a function in a particular family of functions. And then later on, open that function at given points. Okay, good. So let's walk through 4 important classes of functional commitments. These are the building blocks of many of the modern snarks. Okay, so what are these four important functions? The first one is the one Yupeng already described. This is what's called a standard polynomial commitment scheme. Is everything okay? Oh, there's a laser pointer. Wow, amazing. Amazing. Aha, great. Okay, amazing technology. Okay, great. Thank you. All right, so the first one is a polynomial commitment scheme that allows us to commit to univariate variables of univariate polynomials of up to degree d. And remember, this allows us to commit to such a polynomial. Later, we can open the polynomial at an arbitrary point. And it's important that we also prove that the committed polynomial is of degree at most d. So this is standard polynomial commitments. We'll see constructions in just a second. The next one is what we call a multilinear commitment. Yeah, so a multilinear commitment allows us to commit to basically linear polynomials in multiple variables. And if you're not comfortable with that, let me just remind you that here's an example of a linear polynomial in multiple variables. Yeah, the degree in each variable is at most 1. Okay, so we can commit, in this case, we can commit to a multilinear polynomial and later open it up at a given point. Another example is, just a vector commitment, which allows us basically to commit to a vector and then later open up the vector at a particular cell, right? We all know the construction. This is what Merkle trees will let us do. But you can think of this also as a functional commitment, where the function is basically indexed by the vector. It takes as an input a number I between 1 and d, and outputs a cell of the vector. Yeah, so that's another way, just another example of a functional commitment. And finally, the fourth example I'll mention is what's called an inner product commitment. These are sometimes called inner product arguments, which allows you to commit to a vector. Then the verifier will give you another vector, and the prover will prove that the inner product of the committed vector and the given vector is equal to a particular value. Okay, so we have 4 families of functional commitments, and all of these can be used to build snarks. See, these are building blocks for building snarks. Now, why do I separate the inner product commitments, or IPAs? Why did I separate them from the rest? Well, if you think about it for a minute, you realize that the first 3, the domain is actually quite short, right? Members of the domain, doesn't matter how big the polynomial is, how big the degree of the polynomial is, a query is just one element in the finite field. Yeah, so the query is actually quite short. Whereas for IPA, you notice the query is as long as the committed vector, right? I have to give you a vector of the same size as the committed vector. So that generally is the reason why these IPA-based schemes imply slow verifiers, because the verifier would have to construct these relatively large queries. Now, again, there are exceptions, of course, in the literature to all this, but by and large, this is kind of the four functional commitments that we'll be using. Everybody okay with this? So 4 functional commitments. Great. So now let's look at some constructions for these 4. So on the vertical axis, we have the types of functional commitments. And on the horizontal axis, we'll have the structure that's needed for these commitments. Okay, so if the structure we're given is a pairing, then I listed a couple of constructions. For example, for univariate polynomial commitments, there's the famous KZG construction that requires a trusted setup. There's a Dory construction from 2020 that actually eliminates the trusted setup. Yeah, so it does what KZG does with slightly longer proofs, evaluation proofs, but it eliminates the trusted setup. KZG can be generalized to multilinear commitments, and in fact, we also have inner product commitments from pairings. Okay, so those are families of constructions from pairings. One thing, by the way, that I wanted to mention is, again, if you kind of start to think about these functional commitment families, you realize that there's a lot of interactions between them. One can be constructed from another. For example, it's quite easy to see that you can build univariate polynomial commitments from multilinear commitments. Yeah, there's a direct reduction from one to the other. It turns out there are reductions actually between all of these. So in some sense, they're all equivalent to one another. It's not too surprising because all of these can actually imply snarks. But there are also direct reductions between them. Okay, so if we give us pairings, then these are the families of constructions. If all we have is a group where is a cyclic group where discrete log is hard, so no other structure, just a cyclic group where discrete log is hard, then again, we can build these functional commitments. These constructions are called the bulletproof constructions due to Boons and Boodle et al. And the only downside of these is they're only based on discrete log in the random oracle model, but they do require a linear time verifier. Yeah, so they lead to generally short proofs, but with a slow verifier. If we look at vector, if all we have is a hash function, yeah, just a hash function, of course we can build a vector commitment just using Merkle trees, but it turns out using more sophisticated techniques like FRI and breakdown and Virgo and Orion and so on, we can actually build commitment schemes for other types of families as well. Yeah, so we have even more constructions for functional commitments just using hash functions. And again, as Yupeng mentioned, these actually lead to relatively long proofs because the opening proofs for these functional commitments are actually quite large. Okay, so that's with hash functions. And the last family I'll mention is if we have a group of unknown order. And it turns out using groups of unknown order, like for example, working modulo an RSA modulus or working in a quadratic class group, these are examples of groups of unknown order. We also have functional commitments. These are called dark and do. Do basically has shorter proofs than dark, but we can do that as well. Yeah, somehow the first three are quite heavily used in industry. This one has actually not been adopted in industry just yet, perhaps because, well, actually, I guess Chia is using some of this, but not in this particular way. But they have not been adopted widely in industry, possibly because of the mathematics involved. Yeah, so these are the examples of constructions that we have. By the way, for inner product arguments, I do have to mention this beautiful paper by Ishai Kuselevich and Ostrovsky from 2007. This is called the IKO paper, that it also introduces the idea of inner product commitments and uses them to build snarks. Those snarks are quite large, but again, this is kind of a very early paper that kind of shows the power of these techniques. Okay, very good. So now we have functional commitments, and we see kind of the different families of constructions from them. By the way, I should say that there are also constructions from lattices, which I think we're going to hear in the next talk. So I won't discuss lattices here. Okay. So so the reason for the dragon is that in some of these constructions, again, this is where all the cryptographic complexity is hidden. Yeah, so some of these constructions can only be proven secure under fairly strong knowledge assumptions and so on. So there are kind of dragons hidden in the security analyses of some of these schemes. But once we accept these constructions, the rest of the snark construction is actually quite clean. So that's kind of where we're going. Okay. Maybe I should also say, by the way, there are many constructions that could fit on this slide. I couldn't fit so many acronyms. So so this is why I say this is only a small sample. If your favorite polynomial commitment scheme is not on the slide, my apologies. Just there was literally no room because there's so much work going on in this space. It was hard to kind of fit everybody on one slide. So this is just a sample. There's a lot more going on. If you want to see other constructions, please take a look at the bibliography that I cited at the beginning. Okay, so let's go back to the paradigm. So now we have a commitment scheme for functional commitment schemes for functions in a particular family of functions F. We're going to combine this with an interactive oracle proof that supports also function families in this family. And in some sense, you can think of the interactive oracle proof as a way to lift snarks for the function family F to snarks for general circuits. Yeah, in some sense, these are completeness theorems that show that, for example, if you have a polynomial commitment scheme, you can lift that to a snark for arbitrary circuits. Yeah, it's literally a completeness theorem for example, univariate polynomials or for multilinear polynomials and so on. So that's the second component. Let's look at what an interactive oracle proof is. Yeah, so let's generalize this. This is our second component. So let's see how this works. Okay, so again, we're going to fix our circuit. Yeah, so and we're going to fix our input just for simplicity. So the statement X in the circuit, let's fix it just so that it's easy. Now, an interactive oracle proof using a function family F is basically a proof system that has a very particular shape. Yeah, that's the requirement. So what is the shape? It's a proof system that will prove that CXW is equal to 0 for a W that the prover knows, but it does it in a very particular way. So what it will do is, again, it will run through the setup algorithm, but the setup algorithm will output verifier parameters that are actually, the parameters are just oracles to functions. Yeah, so these are basically oracles to functions in our function family. So this takes a little bit of abstract thinking in that, of course, when we instantiate things, we're going to output commitments to functions. But at this level of the conversation, I want you to think of these as actual oracles for these functions that are just available to the verifier to evaluate. But they're not, they're basically, again, they're abstract oracles. All right, so that's the setup. What does the proof system itself do? Well, it kind of does what you would expect. It sends an oracle over to the verifier sends back some randomness, sends another oracle to the verifier sends back some randomness, and this goes on and on and on until the prover is satisfied, and then eventually the verifier will just run this verification test where it can access the oracles in the parameters and the oracles that the prover sent, and it's given as inputs the statement X and all the random values, and it decides whether to accept or reject. And now this is a kind of an algebraic verification procedure that basically is a fast algorithm that either accepts or rejects, and that basically is that's it, right? That's all the verifier will do. It just queries oracles and decides whether to accept or reject the proof. Yeah, so again, an IOP is basically a kind of a proof system that has this very, very particular shape. Again, we can require, I wrote down the requirements for them. Again, it has to be complete, knowledge, sound, and zero knowledge. When we talk about knowledge soundness here, what the extractor is actually given the actual polynomials that the prover sent, and its job is to output a witness. Yeah, this is, by the way, why it was important that the functional commitment is a proof of knowledge, so that when you use the IOP, you can extract the functions from the prover. You can extract the functions f that the prover sent from the prover, and then give those functions to the IOP extractor. All right. So this basically gives us the snark, and we can combine these two things together, the commitment scheme and the IOP, to actually get a snark. Maybe one thing that I'd like to say is that these IOPs actually, first of all, I should say that they were defined in a 2016 paper by Bensasson, Chiesa, and Spooner. So it's a very, very clever, very, very useful abstraction. So everything we think of these days is in terms of these IOPs. It's a very useful abstraction to think about. For those of you who are familiar with PCPs, I should say that basically what IOPs do is it's a generalization of a PCP, where a PCP only allows for one round of interaction of this type, whereas an IOP allows for many rounds of this type of interaction. Good. So now that we understand functional commitments and IOPs, we can put them together to actually construct snarks. So we have a whole bunch of IOPs that have been constructed from univariate polynomials, multilinears, from vector commitments, and so on. Yeah, many, many IOPs. Again, these three dots are doing a lot of work for us here, because there are lots of IOPs in the literature. I couldn't fit all the IOPs on this slide. So again, the three dots represent a lot of work out there. But we can combine these now with appropriate commitment schemes, functional commitment schemes, and we get a whole bunch of snarks. Yeah. So again, this is kind of trying to put order into what UPenn was presenting, in that you can literally think about building an IOP for a particular function family, combine it with a functional commitment for that function family, you put those together, and you get a snark. Yeah, so it's a very clean way to think about all these constructions, very nice and modular way to abstract things. So far, so good? Yeah, so this is an important point to keep in mind. This is a clean way to think about these constructions. So now that we understand that, let's focus on one particular IOP. Yeah, so the IOP that I want to focus on is the Planck IOP, which is very widely used in industry. It's very widely used, I guess we saw this in Yupeng's talk. It's very widely used because it produces short proofs. It has a universal trusted setup, so you only have to run the setup once. And it's really flexible. And by flexible, I'll explain what I mean in just 1 second. Yeah, so let's focus on this one particular IOP. If we combine it with a univariate polynomial commitment scheme, we'll get the Planck snark. Good. So let's fix a finite field, and let's fix an element of the finite field. We'll call it omega, because it's a root of unity. So I'd like to denote it by omega, and we'll say omega has order, which is 3 times the size of the circuit plus the number of inputs. Yeah, this is just for convenience. We'll see why that's needed in just a second. And let's say that, that capital omega is the subgroup of the finite field that's generated by little omega. Okay, so just keep that in mind. And let's see now what Planck does. So again, this was very clear, I think, from the previous talk. All of these results, all of these snarks, what they do is they take a computation, they encode it as polynomials, and then they prove that these polynomials are 0 over a certain set. Yeah, so everything is about encoding things as polynomials. So let me very quickly go through what the Planck arithmetization is. I don't want to repeat what Yupeng said, but there is an important point that I'd like to make, which, again, if you fix a circuit, so here's an example of a circuit. In Planck, the circuit doesn't need to have just addition and multiplication gates. It can have, in addition, it can have custom gates. And here's an example of a custom gate that computes something that's not additional or multiplication. You could construct it from additional or multiplication, but itself is not addition and multiplication. It could have more complicated custom gates. In fact, a very common custom gate is what's called a lookup gate, where you can verify that the input belongs to a certain table. So you can have a circuit with these custom gates. The first thing we do is, I wrote down an example of a computation. The first thing we do is we encode the computation trace as a sequence of triples, right? So again, you saw this in the previous talk. We have a triple for every single gate in the computation. And of course, the output of the last gate is the output of the computation. Okay, very good. So far, so good. So we encode the inputs in here. We encode every gate as a triple. And all we have to do now is all we have to do is encode things as polynomials. So how do we encode things as a polynomial? Again, let me just quickly remind you. We have this one polynomial, which I'll call m. In this case, it's a univariate polynomial. What it does is it encodes all the inputs. So we'll encode the inputs, let's say, at negative powers of omega. So omega to the minus j encode the jth input. And we'll encode all the gates basically using the positive powers of omega. Yeah, so you can see that omega to the 3l encodes the left input, 3l plus 1 the right input, and 3l plus 2 encodes the output. Okay, so you can see that each one of these powers of omega, these 3 powers of omega, encode one row in our table. Yeah, the 2 inputs and the output of the circuit. Great. So so now we have a polynomial. What the Planck IOP does is basically the prover will send an oracle for this polynomial. Yeah, so we send an oracle to the verifier, and then we just have to prove to the verifier, the prover has to prove that this M encodes a valid computation trace of the circuit. And all the idea in Planck is basically how do we prove that M is a valid computation trace of the circuit. So we have to prove that all the gates were computed correctly, and we have to prove that all the wires were encoded correctly. Yeah, this is called a gate check and a permutation check. Yeah, so those are the 2 steps, basically the 2 steps of Planck. Yeah, I'm not going to go through this. Actually, Yupeng went through that at a high level. But so far, so good. So all we did is really we took the table, the computation trace, we encoded the computation trace using this subgroup omega of the finite field, and that gave us that gave us a polynomial, which we prove is valid. Well, all right, so now once you understand the Planck IOP, you can start generating lots and lots of different snarks. So for example, if we pair the Planck IOP with a pairing-based polynomial commitment, we end up with an implementation of Planck, which common libraries actually implement. If we take the Planck IOP and we pair it with the bulletproof, a discrete log-based polynomial commitment scheme, we get, so this is discrete log-based polynomial commitment scheme, we get Halo 2. Yeah, so that the Halo 2's implementation is literally just Planck paired with a discrete log-based polynomial commitment scheme. If we pair it with the FRI-based polynomial commitment scheme, we get Planck 2. Yeah, so you can generate a whole bunch of snark systems just by pairing this one IOP with different polynomial commitment schemes. Does that make sense? So we can get lots and lots of different implementations of snarks based on the same IOP. Why do people like this IOP? Again, because it's very flexible, short proofs, universal setup, allows you to use custom gates. Yeah, so it has lots of nice properties. So it's interesting to try and instantiate it in different ways. And you see we get very different instantiations of these snarks, and they each have different properties. For example, the bottom 2 require no trusted setup at all. Slightly longer proofs, maybe Halo, the proofs actually take a long time to verify, but but they have trusted setup, so you can kind of choose which one you want based on your application. Great. So that's basically instantiations of Plonk, and the problem is we're not done. Yeah, we're not done. Unfortunately, Plonk is kind of not the end of the story. There are problems with Plonk. Again, we saw this in the previous talk. So one of the problems is that actually Plonk does require an FFT in order to compute this polynomial M. That was all based on polynomial interpolation, which requires an FFT. FFTs it's a very fast algorithm, but it's only quasi-linear, right? There's a log S term in computing the FFT, whereas everything else in the Plonk system is linear in the size of the circuit. Yeah. So the FFT step is quasi-linear, everything is linear, so it doesn't take much to realize that if S is sufficiently large, right, the log S term is going to start to dominate the rest of the computation. And in fact, when S gets to be, I don't know why I wrote 2 to the 20 here, when S gets to be around 16 million, the FFT starts to dominate the rest of the computation because of the quasi-linear behavior, also because of memory requirements, and so on. Yeah, so the FFT is becoming problematic. Yeah, so this is one problem with Plonk. The other problem with Plonk is we said, remember, that it supports custom gates. Yeah? Well, one issue is it does allow you to support custom gates, but if you have a custom gate of degree D, then the entire running time blows up by a factor of D. This is because the gate constraints, its degree, now increases by a factor of D. So you can only support custom gates of relatively low degree. All right, so those are two issues with Plonk. Okay, so what do we do about that? How do we solve that? Well, we can try to design a different, or we can try to adapt Plonk to a different settings that would actually avoid these two problems. And that's actually where hyperplonk comes in. So hyperplonk, basically, I should say this is joint work with Boons, Bin Yi, and oh boy, okay, and C. Okay, so right, okay, fine, whatever. So hyperplonk is basically an adaptation of Plonk to the Boolean hypercube, where instead of using finite fields, what we're going to do is we're going to encode elements over the Boolean hypercube. Yeah, it's called hyperplonk because it's literally the same as Plonk, just encoding elements on the Boolean hypercube. The problem is that this is not easy. This transformation actually runs very quickly into problems. One problem that comes up when you do this is it turns out Plonk actually relies on an ordering of this group omega. Yeah, in omega, we have an ordering induced by powers of little omega. Yeah, little omega induces an ordering of this capital omega. On the Boolean hypercube, it turns out there isn't a natural ordering of the elements, and so we have to change how Plonk works to actually deal with these subtleties of the hypercube. I don't think I'm going to get into the details here, but I'll just say that there are some difficulties in transitioning it to the Boolean hypercube. But the benefits of doing this is on the Boolean hypercube, it turns out that the polynomial commitment schemes no longer require an FFT. Okay, so this eliminates the need for an FFT in Plonk, and this is actually also the point of Hyrex and Libra and Spartan. We can do polynomial commitment schemes on the hypercube without an FFT, or I should say multilinear commitments, where the openings and zero tests don't require an FFT. But what surprised us, this was kind of an interesting point, is all of a sudden now we can support custom gates of much higher degree. In particular, if we want to have a custom gate of total degree D, you notice before with Plonk, everything blew up by a factor of D. Now things only blow up additively, almost additively in the degree D rather than multiplicatively. Yeah, so it turned out to have another benefit for custom gates, which was kind of interesting. And just to illustrate this point further, if you look at the implementation, so I should say this is an implementation done by Espresso Systems. And so the proofs, of course, are longer because proofs on multilinear, evaluation proofs on multilinear polynomials result in longer proofs, but not terribly long. What's interesting is that the running time actually is already, even for a simple, not quite optimized implementation, the running time is already lower than an optimized Plonk system. Yeah, so actually moving to the hypercube really does actually provide some performance benefits. So I don't know, this was quite interesting, and there's probably more room for improvements to come. Okay, so the other property, like I mentioned, if you move to higher degree custom gates, in Plonk, this would slow everything down by a factor of 32. In HyperPlonk, as we said, the slowdown is much lower. Okay, so how are we doing on time? I think actually maybe this is a good time to stop. I was going to tell you a little bit about zero knowledge in the multi-party settings, but I think I will skip that. And so, yeah, let me stop here and see if anybody has any questions. Let me skip over these slides, and I will stop here. So thank you very much. This was fun to present. Yeah, please.
Okay. Thank you very much. If we're considering these snogs for these blockchain applications that we talked about at the beginning of the day, who should run the trusted setup?
Oh, bye. Okay, how to run the trusted setup? That's a fantastic question. Right. I think this is actually, honestly, I think this is a question that the industry has kind of grappled with and somewhat answered in recent times, right? So generally, we run a multi-party computation. And then destroy the machines that were part of the multi-party computation, right? So people throw them off of airplanes, they smash them with hammers. It's kind of fun to watch these videos. Maybe I'll mention one more point, which was, thank you for asking, which was another way to run this, this trusted setup is actually on the chain itself. Yeah, so we call this, we call this the power to the people construction, where you can actually post, this is by the way due to Valeria Nikolikanka and Sam. So you can actually run post data, trusted data on chain, and let people come and update the trusted setup as they join, and that adds transparency because everyone can verify that everybody really did participate. In particular, maybe I should say the reason to run it on chain is you guaranteed there was no censorship. Yeah, so if someone honest wanted to participate, if you just do an NPC, you can say, well, maybe the system prevented the honest person from participating, and as a result, there's a majority of dishonest people in the computation. When you do things on-chain, the property of the blockchain is it provides anti-censorship, so you guarantee that honest people were not prevented from participating in the computation. So I'll just plug that as two approaches. So one is doing it as an NPC off-chain. The other one is actually using the chain to guarantee that there was no censorship on who can participate in the trusted setup. Yeah. So thank you for asking that question. It's a very good question. Great. So thank you very much.
Yeah, thanks, Dan, for this amazing overview, amazing talk. Thanks, everyone. So now we're going to take a 15-minute break. And also, so we do have an overflow room. So for people who don't have seats, we have an overflow room in 405 Soda Hall. So it's just right around the corner. Great. Thanks, everyone. All right, so we'll see everyone back at 11:05. Oh, 10-minute break. So we'll see everyone back at 11:05. Okay. Hi, everyone. We are trying to get started. Could you take a seat, please? Hello. Hi, everyone. Please get seated. We're getting started now. Can everyone stop talking? Can you take your seats, please? And also, we have a lot of people here today. So we have the overflow room 405. So that one is full. And we have another overflow room, that's a 306. So if you can't find a seat here, and you cannot find a seat in 405, you can go to the room 306, which is downstairs. And also, it's best that people don't use the front door during the talk so that you don't interrupt the rest of the audience. So please use the back door, and then we have side doors also. People in the back, could you please take a seat? And we are trying to get started now. Can people tell the people in the back, if you don't have seats here, please, you can go to the overflow room. And if you have seats here, please take your seat. We are getting started. We have a lot of talks today, so we need to get going. Okay, so.
Okay. Hi, everyone. Hopefully, all of you are enjoying your day. So for the next talk, we're going to have Abhishek Jain, who is an associate professor at Johns Hopkins, and he's going to tell us about recent developments in snarks.
All right. Hi, everyone. Thanks for coming. And so this talk is going to be a slight departure from the previous two talks in that the focus here will be mostly on the theoretical advances in snarks. So essentially zero-knowledge proofs where I only focus on the succinctness property. Okay. And the focus here is on what assumptions can we build these objects from. So let's get started. So we've already seen what snarks are, so I'm not going to repeat the definition, but just very briefly, what we care about is the proof size and the verification time to be very small. In particular, the verification time should be much faster than computing the proof from scratch. So the agenda is to figure out what assumptions we can build snarks from. And this is obviously a very, very broad area of research with hundreds of papers over the last 2 or more decades. And I'm going to cheat because I have limited time. I'm only going to focus on essentially research that has happened in the last 1 year or so. But let me just do a very brief recap of what we have known in this line of work for the past many years. So as we've already seen from the last two talks, we do know how to build snarks from a variety of tools. And in fact, we know how to build them for general NP languages. Broadly speaking, we can essentially categorize most of these works, or essentially all of these works, into one of the following two categories, if not both of them. So the first category essentially says that we can build snarks for NP by starting from some interactive protocol, typically in IP or IOP, and then round collapse it using the random oracle. Okay, so the idea is that all the challenges that the verifier sends in the protocol, they can now be computed using a random oracle. So on the plus side, this gives you proofs in the transparent model, in the transparent setup model. On the negative side, and again, the focus of this talk is on assumptions. So on the negative side, the problem is that in order to use these systems, you have to instantiate the random oracle with a hash function, and this results in heuristic security. The other side of things is where we can use some form of extractability assumptions to build snarks. So most of the works use something called knowledge of exponent assumption or variations thereof. And again, theoretically, there is a slight problem when you use such assumptions in that if you think of security proofs as sort of a construct, there is a missing subroutine in the construct when we do these proofs. We just assume that such a step in the proof exists, but we don't know how to actually build that step. Right? And in fact, in general, when you use such assumptions, we do know of some implausibility results that such assumptions don't exist in general. Again, I won't get into the details of that. So the question is, must we rely upon non-standard assumptions to build snarks? And to an extent, this seems inherent. Almost a decade ago, Gentry-Wicks showed that actually if you want to build snarks for NP, then you must rely upon some form of non-falsifiable assumptions. I won't get into what that means, but essentially some form of non-standard assumptions. There are some caveats to these results, to this lower bound, which if I have time, I might get into towards the end of the talk. But this essentially says that some form of non-standard assumptions are sort of inherent. So if we want to actually build snarks from standard assumptions, we essentially only have two paths forward, it seems. So one could be that instead of focusing on general NP, I could focus on some useful subclasses of NP and try to build snarks for such subclasses from standard assumptions. The other route would be to sort of exploit the caveats, and again, I haven't mentioned what those caveats are, to try to overcome this impossibility result. So for most of the talk, I'm going to focus on the first direction, which is trying to build snarks for some useful subclasses of NP from standard assumptions. Okay. So the first class that I want to talk about is what is called batch NP. So what is this class? Intuitively, instead of proving a single statement, I want to prove a batch of statements. Okay? So let's say I want to prove some case statements. I think there is some of the symbols got messed up, nevertheless. So so the prover wants to prove, let's say, k statements to the verifier, k NP statements to the verifier. And now instead of the standard efficiency requirement for SNARKs, here what I want is that the proof size should be much smaller than the total witness length of the k statements. So ideally, maybe just the size of a single witness plus some additional overhead. So this class of NP is already very useful for applications to rollups, to building aggregate signatures, and other objects. Okay? And it turns out that here the Gentrevic's lower bound does not apply. The other class is just focusing on deterministic computations rather than non-deterministic computations. So this is P. And again, this class is obviously useful for just basic delegation of computation applications, and in fact also for other cryptographic applications like verifiable delay functions. Okay, so last year what we showed is that for these subclasses, and in fact some related subclasses as well, which I won't get into today, we can actually build SNARKs from standard assumptions. In fact, we can build it from the learning with errors assumption, which means that if you assume post-quantum security of LWE, then you also get SNARKs with post-quantum security for these subclasses. And asymptotically, the efficiency of these proofs is more or less what you would want. It's just polylogarithmic in the computation time. Okay, good. I will talk about concrete efficiency a little bit later in the talk if I have time. Okay, so in fact, in this work and also another work by Kalai, Vaikunnathan, and Zhang, they showed that in fact, more or less, you should only care about building SNARKs for batch NP. Once you have that, then you can build it. Then you can build SNARKs for many related classes like P, bounded space NP, and so on and so forth. So for this talk, you can just focus on batch NP, and that should be enough. Okay. So in fact, since that work last year, there have already been many follow-up works where it was shown that you don't even need necessarily LWE to build these SNARKs. You can in fact build them from standard group assumptions, like you can build it from DDH plus QR, or you can build them using bilinear maps, so standard assumptions, decision linear assumption on bilinear maps. And more recently, we showed that you can in fact even build it from DDH. Okay, so in fact now, if you combine all of these results, this is basically saying that if you want SNARKs for these subclasses of NP, you can build it from most standard assumptions in cryptography that we care about, which is great. Okay, so what I want to show you is essentially a general paradigm that has been used for most of these results. And that paradigm is what is called the correlation intractability approach. And to explain this idea, I want to first recall the Fiat-Shamir approach. Okay? So this is an approach that is used in the design of many SNARKs, in fact, even many practical constructions of SNARKs. So what is the idea? So the idea is that you start from some interactive protocol where the verifier's messages are just random strings, so it's a public coin protocol. And now you want to compress it into a non-interactive protocol. And the idea is that now instead of having the verifier send the challenges in the protocol on the fly, you just compute them non-interactively using a hash function, which you model as a random oracle. So now the prover can just compute this entire proof in one shot and send it over to the verifier, and the verifier can verify it as before. And if the hash function really behaves like a random function, a random oracle, then you can prove that the resulting non-interactive protocol is still sound if the original protocol was sound. Okay, so a very natural idea to try to build SNARKs in the standard model, so without random oracles, but let's say just using a common random string, would be to try to somehow instantiate this random oracle with some concrete hash function. Okay? And not just assume heuristically that it works out, but rather actually prove security of this non-interactive protocol. So in general, this idea of securely instantiating the random oracle, we know that there are many barriers to it. In some cases, there are impossibility results that you can't do this in general. Nevertheless, for some specific cases, a possible route towards secure instantiation of random oracles was actually proposed many years ago, but only recently have people started, coming up with solutions to do this instantiation. And the idea is to use a special class of hash functions which are called correlation interactable hash functions. So what are these hash functions? Roughly speaking, these are hash functions that avoid bad correlations between the input outputs of the hash function. So the idea is that it's a family of hash functions, again, keyed hash functions. And the idea is that a PPT adversary, when given a random member of this family, the description of a random member of this family, he should not be able to find an input x to the hash function such that the output of the hash function is equal to the evaluation of some function f on this function. And this function, on the input, sorry. And this function f is the function on which we say that this hash function is correlation interactable. Okay? So essentially, again, we are saying that hash function is correlation interactable for a family of functions, let's say f. You can generalize this to relations as well, where essentially a cheating prover or a cheating adversary cannot find an input such that the output of the hash equals the output of the function f on this input x. Okay? So this is the notion of correlation interactable hash functions. And now, of course, we can, just syntactically, we can instantiate the Fiat-Shamir paradigm using correlation interactable hash functions, just as before, right? So now, instead of having the verifier send the random challenges on the fly, we just compute them using the hash function. And the description of the hash function, or rather the key, is as part of the CRS, the common random string. Okay. So now the question is, why is this sound? If I do something like this, why does it result in a sound non-interactive protocol? So here is the idea, and this is a simplified scenario. So suppose the public coin protocol that we started with is special sound. In the so a consequence of protocols that are special sound is that for every first message, let's say alpha, there is a unique challenge of the verifier, a unique beta, such that there is an accepting gamma, an accepting third round message that can lead to an accepting of the proof. So now if you have for every alpha a unique beta, then you can just define a function called bad function, which essentially maps the first message alpha to this challenge beta. And again, this is a bad function because it's basically saying that for any alpha, there is this particular bad beta that would lead to an accepting proof. Okay? And of course, this is for the case when the statement is false. Right? Okay. So now, suppose that we actually instantiate this Fiat-Shamir paradigm using a correlation interactable hash function, which is actually correlation interactable for this bad function. Okay. So now, if this is the case, then you can see that if there is actually an accepting proof, alpha, beta, gamma, then by definition, beta is the output of this hash function. But on the other hand, we know that the beta is actually also equal to bad of alpha, right? So this gives a contradiction to the correlation interactability property, right? Because now we have that the output of the hash on alpha is equal to bad of alpha, right? So this gives a contradiction. So this is why this approach results in soundness. So essentially what it says is that now I could design non-interactive proofs by starting from some interactive protocol and then applying the Fiat-Shamir approach, but except of using random oracles, I'm going to use this special hash function. Okay? So in fact, this is a general recipe for round compression. You start from an appropriate public coin protocol that you want, depending on what application you care about. Now you have to design a correlation interactable hash function, which is correlation interactable for the bad relation that is defined for that public coin protocol, and then you marry them together in the manner as I showed before. So in fact, this approach has been very, very successful, not just for building snarks, which is the focus of this talk. It turns out that it can be used for building non-interactive zero-knowledge proofs. So even if you don't care about succinctness, but you want just zero-knowledge property, this approach is very powerful. In fact, it led to breakthrough results in this regime, the first construction of non-interactive zero-knowledge from LWE. It's also useful for building verifiable delay functions and many other theoretical results in, for example, establishing hardness of certain complexity classes and so on. So very, very successful approach. In the case of snarks, if we want to rely on this approach, it's very clear that we have to add an additional property on our first step. So we need to start from a public coin protocol, which is already succinct, right? This compiler does not add succinctness, it preserves succinctness. Okay? So we need to start from a protocol which is already succinct. So this creates additional challenges when we want to build snarks. And I just want to give you a very brief overview of why there are additional challenges when we want to build snarks. Okay, so a very natural candidate for realizing this approach would be, let's say, we take the classical Killian protocol or variations thereof, right, and then somehow round collapse it using an appropriate correlation intractable hash functions. I haven't told you, what assumptions we can build correlation intractable hash functions for, but you can trust me, we can build them from standard assumptions, let's say learning with errors, and even for many cases from TDH and so on. Okay, so this would be a very natural route. Turns out, we can't really do this. There are, in fact, some barriers. There are some lower bounds that people have shown. And again, this should not be so surprising. If we could really do it, not only would we get snarks for, let's say, P or batch and P, we would get snarks for NP, right, from standard assumptions. So it's not so surprising that we run into problems when we try to use this approach. In fact, there's a bigger issue here, or a broader issue here. The point is that Killian or family of protocols are computationally sound, or in other words, they're argument systems, whereas the definition of correlation intractability is really designed to work for statistically sound proofs. Okay? And therefore, there's a mismatch in this kind of approach. It's not quite clear how to extend the definition of correlation intractability to actually account for computational soundness rather than statistical soundness. Again, the problem being that in the case of computationally sound protocols, for every alpha and beta in this 3-round protocol that I described, for every alpha and beta, there could exist an accepting gamma. And this just does not work with correlation intractability, which is more defined for sparse relations. Okay, so we can, of course, take the route of trying to build succinct interactive proofs, right? So protocols which are already statistically sound. And in fact, this is an approach that was taken in some works, some prior works. So what these works did is they started from the GKR protocol that Yupeng talked about, which is for bounded depth computations. And then using this correlation intractability framework, they showed that you can actually build snarks for bounded depth computations from the learning with errors assumption. Okay? So this is great. At least for, let's say, NC1, we can build snarks from standard assumptions. But if we want to extend this route, then we run into issues. So in general, succinct proofs for all of P are unlikely to exist. And succinct proofs for batch and P are also not really known. We only know them in some special cases, but there are some major bottlenecks towards building these objects. So now I've told you this long story about trying to use correlation intractable hash functions for building snarks, but it seems like we have run into a fundamental bottleneck here. So I'll just show you like a glimpse of the way around it, and without getting into details. So the way around it is to actually not use fully computationally sound proofs or fully statistically sound proofs, but sort of something in between, what we call somewhere statistical soundness. So the idea is that these proofs are statistically sound in some locations. So you can think of the protocols as operating in some CRS model. Okay? The idea is, and again, we are concerned, let's say, in the batch NP setting. So the prover is trying to prove that K statements are in some NP language. All of them are true. And the idea is that in the CRS, you can actually program an index, let's say I. And the idea now is that for that index I, no matter what the cheating prover does, even if he's unbounded, he can't prove a false statement at that index. Okay? The other indices, I don't care about it, but for index I, he cannot prove a false statement, even if he's computationally unbounded. And it turns out that this is good enough for applying the correlation intractability framework. The idea is kind of natural. If you are trying to prove a construction is sound, the point is that for batch NP, if the batch is not true, then it means that there is at least one index I where the statement is false, and that's good enough, right? Because at that index, I can leverage the statistical soundness of this of this interactive proof system, and this allows me to now use correlation interactability. So this is sort of the conceptual way to get around these things. Now, of course, there's a lot of work involved in building interactive protocols with some way statistical soundness. Not going to show you how they work, but at a very high level, they still follow the general template that Yupeng and Dan talked about, where you start with some interactive protocol. Instead of using functional commitments, you are going to use a very special form of vector commitments, what are called somewhere statistically sound, somewhere statistically binding commitments in order to have this kind of property. The other challenge is that you can't actually get compression as is. You have to actually develop new ideas to kind of achieve this kind of statistically sound compression, because of course we didn't know anything beyond GKR for all this time, so you have to actually bake in new techniques for achieving compression. So that's a topic for a separate talk, which I won't get into today. But the point is that there is a way to build these somewhere statistically sound proofs, and you can achieve them. Okay, so a note about efficiency, right? So how efficient are these? So asymptotically, they're fantastic. Okay, so asymptotically, we can achieve as good efficiency as we could essentially hope for. In fact, we can even have rate 1 proofs. This was done in some recent works this year. So by rate 1, I mean that even the overhead of security parameter is only additive, not even multiplicative. So asymptotically fantastic. Concrete efficiency, well, a lot of work needs to be done. So there are several issues in these constructions in terms of concrete efficiency. A, they make non-black box use of cryptography, so not ideal in that sense. And they also use heavy tools. So the correlation interactable hash function constructions that we presently know use very heavy tools like FHE, et cetera. So there is a lot of scope for improvements in this direction. We could obviously ask the question, must we use this general template that I've described to you? Can we just avoid it and use a completely different approach? And indeed, there is a recent amazing work of Waters and Wu that shows that you don't have to follow this template. If you have bilinear maps, then you can actually build snarks for batch and P, and then using our compiler, also go to snarks for P. Without using correlation interactability, in fact, without using PCPs, it essentially goes back to the roots, goes to old constructions of non-interactive zero knowledge, and then shows how you can get rid of the zero knowledge property and then somehow batch multiple proofs together. So really nice. So maybe that's a direction for trying to get more efficient constructions from standard assumptions. Okay, so do I have 1 more minute? Or right? Okay, so maybe I'll have just 1 or maybe 2 slides about NP. Right, so I showed you we can build these objects now from standard assumptions if we focus on subclasses like P or batch and P. So what about NP? So Gentry-Wicks did show us that in general we can't achieve snarks for NP from standard assumptions, but with a few caveats. And I won't get into the first 2 caveats, which is what people usually focus on. In some sense, the key point of Gentry-Wicks is that you can't build snarks from standard assumptions unless the reduction, the security reduction that we are trying to build in the security proof can actually determine whether the statement that the adversary is trying to come up with the accepting proof for, the false statement, is actually false. In some sense, the crux of their lower bound is that a cheating adversary could maybe just, instead of proving a false statement, he could just prove a true statement, and we can't know. So that's sort of the crux of the lower bound. And so the question is, can we actually somehow leverage this caveat to build snarks for NP from standard assumptions? And in fact, we do know of snarks for NP from indistinguishability obfuscation. And in fact, if you instantiate this construction from, let's say, the recent breakthrough work, which constructs indistinguishability obfuscation from well-founded assumptions, then you do get snarks for NP from falsifiable assumptions. But the caveat, the reason why this works, right, is not because of things like adaptivity, black box reduction, non-black box reduction, nothing like that. The reason it overcomes Gentry-Wicks lower bound is because the reduction runs in exponential time and just simply decides the language. Okay? So essentially, what it's showing is that by building an inefficient reduction, I can actually overcome Gentry-Wicks. There are some negative consequences of this, which I won't get into, but this does leave open the question that must I use obfuscation, which is a very powerful hammer? Can I actually leverage this aspect of building inefficient reductions to build snarks for NP from other assumptions? And I think that's where I will end. So in summary, we do know how to build snarks from standard assumptions now, at least for some subclasses. But in terms of concrete efficiency and building snarks for NP from standard assumptions, still many open questions. Thank you.
So I think you mentioned this, you have to create this collision in...
Interactable hash function.
Yeah, interactable hash function for this bad function.
Yeah.
I think the bad function would depend on what circuit you want to prove, right? So you want to create a new hash function for every instance of the...
In general, the way, yeah, I mean, in principle, you're right, but in general, we design these protocols for, for some universal language, right? So, we can build these for circuit satisfiability, and then, you are essentially done in that case, right? Yeah.
Yeah, so like a related thing is what is like the cost of finding this hash function itself?
No, so indeed, the reason why this approach currently is not concretely efficient is because the construction of such correlation interactable hash functions are very expensive. So one of the construction uses fully homomorphic encryption. And and in fact, in very expensive ways, in the sense that where inside fully homomorphic encryption, you are computing some other cryptographic, performing some other cryptographic operation, for example, doing decryption of some encryption scheme. So it's a very expensive process, which is why these objects are concretely not so efficient yet, but assumptions-wise, yeah, we are already there.
Yeah.
More questions? It's time to be shaken.
Great. Thank you for the great talk. So next we'll have a list of contributed talks. So I guess given the time limit, please stick to 5 minutes each, and I'll remind you at 1 minute. So I've combined all the slides together, so let's go one by one. And also, Marek, if you're here, you're doing a demo, right? So if great, you can actually do it at the end of this session. Okay. Thank you.
So, hello everyone. My name is Ino. I'm a graduate student here at Berkeley. So I'm very glad to start the very first talk of this session. So far we have seen how to build succinct zero-knowledge proof for, sorry, it just turned on for some reason. So far we have seen how to build succinct zero-knowledge proof for finite field arithmetic circuits, which Yupeng and Dan covered about that topic. But in many real-world applications, such as when we train some machine learning model, what we actually use is floating point computations. So it is a very important topic to build efficient, succinct zero-knowledge proof for all the floating point computations. In this talk, I'll be giving a very general framework to design efficient zero-knowledge proofs for floating point computations. So I will just skip all this. So what is the state of art of doing this? So the main idea is just to reduce proving floating point computations back to just proving computations over some finite field. Okay, so here comes the IEEE standard, which essentially tells a computer how to do floating point computations. Just work with a very simple example. Consider the multiplication between two integers, a and b. First, the IEEE standard says that we should decompose those integers into their bit representation. Then we consider the binary circuit, which first multiply them together. Okay, then we do some rounding operation so that we can trim up some precision to get a final output. The state of art basically says that we should prove that everything here in this picture is done correctly. So we prove that both binary computations are done correctly. The takeaway is that we prove that we exactly follow this IEEE standard. However, there is some significant drawback when it comes to the prover efficiency. To take a very concrete example, for these binary circuits, it could have way more than 8,000 gates. So when a prover wants to prove that all the gates are done correctly, it will have a huge blow up in terms of the prover's running time. So here is our solution. Our intuition is that hopefully all you guys agree at this point that to verify something could be much cheaper than to prove something. So as a computer, when I want to compute some floating point multiplication, say this multiplication between integer a and b, I want to get some output value c, but I don't know what this output value c is. So I follow this IEEE standard simply because it will give me some output value c that is very close to the true value of this multiplication, where the true value is just the multiplication between a times b. But when I want to prove to you that this multiplication is done correctly, I already have some candidate value in my mind as the output. Let's say this candidate value is some integer c star, which somehow doesn't show up here. However, the only thing that I have to prove to you, if you think about it, is not how I get this number. I just want to prove to you that this number, c star, is actually very close to the true value of this multiplication. So motivated by this discussion, we define this notion called the relative error, which essentially just measures the difference between the prover's proposed candidate value and the true value of this multiplication. So it becomes clear that what we want the prover to do is to show that the relative error incurred for every step of the floating point number operation is sufficiently small. So why is this whole model of relative error meaningful? So I would just say that this is meaningful because we can use some techniques in the field of numerical analysis to bound the relative error to ensure good output accuracy. And it also applies to the case of floating point computations. We're able to get some good efficiency improvement using this general framework. So here are some concrete numbers to demonstrate our efficiency. So for 32-bit floating point arithmetic circuit with 2 to the 20 gates, our prover time is actually 57 times faster, and it's even faster for the case of 64-bit floating point computations. That's the end of the talk. Thank you, everyone. Okay, any questions?
I think we'll take questions all at the end.
Okay.
Hello, everybody. So today I'll be presenting the reductions of knowledge framework. And the way you can think about this is that this is a sort of generalization of arguments of knowledge in which the verifier doesn't immediately check a statement, but rather reduces it to a simpler statement to be checked. And the argument I want to make today is that this sort of gives us a modular framework for reasoning about argument systems. So the high-level anatomy of an argument of knowledge is that if it's interactive, we have the case that the prover is trying to prove some witness to a verifier's statement, okay? And the verifier might ask some challenges and questions, and eventually it'll output true or false, depending on whether it actually believes the prover's initial statement, right? But we have recently seen that many modern techniques are actually reductive in their flavor, in the sense that the verifier doesn't immediately check the input statements, but rather reduces it to a simpler statement to be checked. So the example I want to point out today is this notion of a folding scheme, which we introduced earlier this year, which we used to build recursive proof systems. And the core idea of a folding scheme is that a verifier takes as input two statements, okay? And instead of checking either one of them, just compresses them on top of each other to output a new statement to be checked, okay? And it turns out this is quite a useful technique, but we couldn't have defined it using the standard language of an argument system because, we're not actually checking a statement, we're just reducing it to a simpler check, right? But it turns out that we need to define some notion of completeness and knowledge soundness in a way that makes it seem like it's almost an argument system. And it turns out this idea of an interactive reduction sort of is everywhere in the literature, okay? And in some cases, some papers define this notion of interactive reduction for their specific construction that they're building, okay? But in many other cases, these reductions are sort of just embedded in larger argument systems. They don't even have their own specific security definition. And this makes it hard to sort of port these ideas around. So the core point I want to make today is that interactive reductions are a sort of universal notion that everybody knows about. They're sort of folklore. But their definitions are quite ad hoc and vary paper by paper, right? And the lack of a common language makes it difficult to compose compatible techniques hidden under incompatible abstractions. So in an effort to unify this notion of an interactive reduction, we introduce the formalization of reductions of knowledge. At a very high level, a reduction of knowledge, all it does is just capture this notion that you're reducing the task of checking one witness to the task of checking another witness, potentially in a simpler and easier to check language, okay? And just like with arguments, we can define a meaningful notion of completeness and knowledge soundness. So completeness holds if the verifier's initial input U1 is satisfying, then it should be the case that whatever the verifier outputs, whatever the verifier reduces U1 to U2, should also be satisfying. And knowledge soundness holds that if any malicious prover is able to output some malicious W2 that is able to convince the verifier for the output value U2, then it should be the case that it knows a satisfying witness for the initial input U1. And this captures the intuition that it is okay for the verifier to check U2, the output statement, in place of the input statement. And potentially checking U2 is a lot simpler and a lot easier than checking U1. For instance, U1 could be 2 instances of a folding proof system, and U2 could just be 1 instance, okay? So far, I've sort of just described reductions of knowledge as a high-level abstraction that sort of generalizes this idea of an interactive reduction. But the core idea here is that we can also show that reductions of knowledge can be sequentially composed. That is, if you have 2 reductions, one from relation R1 to relation R2, another one from relation R2 to relation R3, then it turns out that you can sequentially compose them. That is, take the output of one reduction and input it into another reduction. And what this means is that we can take a large argument system that's very, very, very complicated and break it down into a bunch of little tiny reductions, okay? And it allows us to give a meaningful security definition for each step of this argument. And as such, reductions of knowledge serve as both a unifying abstraction as well as a minimal framework for arguments of knowledge. Thank you.
Hi everyone, I'm Tiancheng Xie from UC Berkeley, and today I'm going to talk about ZK Bridge, trustless cross-chain bridge made practical. And this is a joint work with Jiaheng Zhang, Zerui Chen, Fan Zhang, Yupeng Zhang, Yongzhen Jia, and Dan Bonnet and Dan Song. So first, let me introduce what is a cross-chain bridge. A cross-chain bridge enables a secure and efficient communication between 2 blockchains here. And this is a critical infrastructure for multi-chain interoperability. Unfortunately, recently there are a lot of different attacks on existing bridges, such as Axial and Wormhole. And basically all of them cause a significant loss, more than hundreds of millions loss. So why does these bridges are vulnerable? Because there are several issues then. First, the trust model and security are problematic. In most of the bridges, they are based on a committee where they require 2/3 of the committee are honest. And this is a huge problem because the committee size usually in a bridge protocol is small. And there are other types of bridge. For example, optimistic bridge, they have performance issue because on-chain verification of a block is prohibitively expensive. So we propose a new protocol. It's called ZK Bridge. And in our new protocol, we minimize the trust. We're moving the trust from a committee-based bridge to trusting correctness of zero-knowledge proofs. And since we are using zero-knowledge proofs, we can get a very high performance using our new efficient distributed ZKP protocol. It's called DVirgo. And on-chain costs can be reduced by batching verification. So additionally, we have several other advantages. For example, our bridge is permissionless and decentralized. Unlike committee-based bridge, we can add provers at any time, anywhere you want. And our bridge allows developers to develop their own application without even notifying us, so they can develop their own cross-chain applications. So due to time limit, I'm not going to talk about the whole architecture of our bridge, but here I'm going to talk about our core part. It's called block header relay. So in block header relay, we have a sender chain and a receiver chain. And what our bridge do is we relay every block header from the sender chain to receiver chain. So the receiver chain can get an idea at least the block hash of the sender chain. And what we do is we use a block header relay network. It's basically a lot of different provers here, distributed provers here, and we generate proof for validity of the block header. And it's usually not so simple to generate proofs, and I will talk about later. So here we use dvirgo to speed up this proof generation. And this is a new distributed ZKP protocol based on the Virgo. And we achieved the optimal parallelization and practical communication. Here is some number here. We did some experiment on tendermint block. And in a tendermint block, to verify a tendermint block, we need to verify a lot of different signatures from the tendermint validators. So here, we experiment the different number of signatures and different number of machines. As you can see, we scale linearly when we increase the number of machines. So our protocol can have a more optimal scale. And the proof generation time here is very, very small. And we basically can prove a block header just slightly above 10 seconds. And here is a concrete number for, and actually here's the end-to-end number for ZK bridge. Here is all slightly above 10-second number. And here, sorry. And we apply the recursive proof here to reduce the on-chain verification cost, and recursive proof does not cost too much. Yeah, thank you so much. And here's our website for more information, and please follow our Twitter here. Thank you. Yeah.
Okay. Right. Thanks, everyone. So following Tianqing's talk on ZK Bridge, we also wanted to talk about a new initiative that the researchers on ZK Bridge is launching. We call it ZK Collective for the ZK Bridge Collective, with the goal to build a secure universal foundation for multi-chain interoperability. So again, the work on ZK Bridge is only just the beginning, and also for more information, you can go to zkbridge.org and also see the latest paper. So with the ZK Collective, here are a list of goals. At a high level, the goal is to build a secure universal foundation for multi-chain interoperability. And more specifically, there is a list of goals that we hope that the secure universal foundation for multi-chain interoperability will achieve. So number one is security. We want it to be trust minimized, as Tianqing already showed. Here, using ZK succinct proofs, we can reduce the trust so that there's no reliance on external trust assumptions. And number two, we hope that with this overall system and this foundation, we also achieve defense in depth. For example, we enable proof diversity. So for each, for example, for each chain, for each bridge in this case, we can actually have multiple implementations of the proof generation and verification, and essentially achieve inversion programming, so that with this proof diversity and multiple implementations, then altogether we can achieve defense in depth. And also, of course, for the whole system, the implementation, we need good smart contract audit and also ZK circuit audit. And with the defense in depth, the proof diversity, hopefully it can also reduce some of the reliance on these audits as well. So that's number one, is to really build a truly secure that's why we call it foundation for multi-chain interoperability, the security. And also we want it to be really efficient, both in terms of proof generation and proof verification. And also want to have a really good user experience, in particular have low latency. And in this case, potentially you can combine it with some optimistic approach to even achieve shorter latency, and you achieve actually the best of both worlds. And also we hope that this secure universal foundation can have really low fees, ideally close to 0 fees. And another important aspect, also as Tianjin mentioned, is extensibility. So with the ZK bridge approach, it naturally actually decouples today's common bridge functionalities into multiple layers. In particular, with the ZK bridge approach, we focus on the base layer. So in the base layer, by doing these succinct proofs and doing relay of block headers, essentially what you allow is you allow the two chains connected by the bridge in this case to just sync the states, the latest states of the two chains. And then on top of that, you can build a lot of other application functionalities and other, in general, rich functionalities on top. So with this ZK Collective, our goal is to actually enable a secure universal foundation for the base layer for this multi-chain interoperability, and to enable an open ecosystem so that other dApps and also other bridges and other bridge aggregators can all build on top of this secure universal foundation as a base layer. And another aspect as universal is so that we can really have this approach to build this foundation for all chains, connecting all chains. And in particular, in this case, for certain chains, depending on how their implementation or specification is for light clients, and also for some of their consensus protocols, we also hope to help certain chains that are not so ZK friendly with certain modifications. In the future, they can be more ZK friendly or proof friendly. And also, essentially, we can help each chain to build up. We didn't have time to talk about it, but for each chain to help them build up what's called state proofs, which essentially can be used to build this ZK bridge. And finally, we hope that this approach in general, this collective can be self-sustainable as well. So for the collective, we have 3 key principles. First is open source and open ecosystem. So all development in this from this ZK collective will be open source, and we encourage the whole community to join and support an open ecosystem. And we view this, since this is a base layer, we view this as a public good. We hope that everyone can help contribute and support this as a public good. And we really want to build this as a collaborative effort, since this can really truly provide a huge utility to the entire community, because I think most of us believe that the future of blockchain is multi-chain, and having the secure universal foundation is key to the success of this multi-chain universe. And so what is really ZK Collective? It's essentially a collection of members of different types, including entities, projects, individuals, and so on, and all come together to achieve this common goal, as I just mentioned. And this collection of members can include, different types, including researchers, developers, L1, L2 chains, other bridges, bridge aggregators, dApps, node operators who want to participate, to be relayers, and also to generate proofs, and also including investors and users and so on. Because again, we see this as a really important utility for the whole community, and hence we hope that the whole community can join into this collaborative effort. And the ZK Collective, in collaboration with its members, aims to conduct a number of different activities, including further research, how we can develop better the state proofs and this ZK bridges, and also ZK technologies to further improve efficiencies and other aspects of this approach. And also, education is really important to provide education to the general community, and also we hope to provide education for users as well, to help educate users that they should demand secure solutions for these bridges. And the ZK Collective will build reference implementations, and also in collaboration with members to help produce production implementation for these systems as well. and to help with the security audit, ZK2 development, and also standardization to, again, help make this a truly secure universal foundation for multi-chain interoperability. And also, as I mentioned, for certain chains, they may not have been designed to be ZK approved friendly. We hope, with the ZK Collective, we hope to help provide new proposals to help these chains to improve, to become more ZK approved friendly. And also, finally, we hope that this can actually be a good experiment for the whole community to see how we can really build a self-sustainable ecosystem for public good. So to summarize, a call to action, please, if you are interested to help, join the collective, spread the word, and also help contribute to different activities. And also, it's an interesting question how to make this effort self-sustainable. So we are open to suggestions on models and support for self-sustainability. And to join the collective, please fill in the form. And we actually have a number of leading L1s and dApps and so on join the collectives already. And we hope more members can join. Great. Thank you.
Perfect. Okay, thank you. So I'll be talking about a new type of Schwarz-Zippel lemma for multilinear polynomials and some applications to snarks from both groups of unknown order and lattices. This is joint work with Benedict Bunz. Forgot to add his name. Sorry, Benedict. So classical Schwarz-Zippel lemma. This is one of the most, a very useful lemma in computer science, right? It says, well, at least a special case of this, it says that if you have a polynomial, it could be a multivariate polynomial, mu-variate polynomial, and you evaluate it at a random point, right? Then what's the probability that it will be equal to 0 over a finite field mod p? So this is less than the degree of the polynomial divided by the size of the sampling set. So in this case would be 2 to the lambda. And this holds more generally for f over any field, not just ZP, or actually any integral domain, but not for arbitrary commutative rings. And we can give like a simple counterexample. Like let's say we were looking at Z2P, and this simple polynomial f of x is equal to px. Okay, so there's a probability 1/2 that that's going to be equal to 0 on a random point in 0 to 2p. So what if we wanted to try to restrict this a little bit more? Let's say we only looked at polynomials that were coprime with n, and we were looking at Zn, okay? Well then at least univariate linear f, so just like a linear function, right? That's coprime to n, meaning the vector of the coefficients are not divisible by n, do not have a common divisor with n. So that we can show pretty easily that is going to have at most one root mod n. But it doesn't really generalize, even if for higher degree, even if we restrict to univariate polynomials. Here's an easy counterexample. Let's say that f of x is equal to x to the lambda mod 2 to the L. So this is going to, again, be equal to 0 on half of the points in this domain, 0 to 2 to the lambda. But inspired by this linear case, we're able to generalize this to multilinear polynomials, where the multilinear polynomial, so now it can be in mu variables, but linear in each variable, is coprime to n, right? Which means that there's no common divisor of n that divides all the coefficients of this multilinear polynomial. So we're able to show that the probability that this will be 0 on a random point sampled from this box 0m to the mu is less than or equal to mu over m, which is the term from what you would get from normal Schwarz-Zippel, plus some error term. Okay, and this error term we can show can be made to vanish for sufficiently large n. And in particular, we can characterize exactly what's a sufficiently large n. We have a theorem that says if we have m greater than or equal to 2, and we have any mu linear integer polynomial f coprime to n, where the number of bits in n is is greater than 8 mu squared plus log 2 mu lambda, then this probability, okay, is less than 2 to the negative lambda plus mu over m. So the error term is negligible in lambda. And we only need to set n such that it's on the order of 2 to the o of mu squared plus log mu lambda. Now we also have an algorithm that's similar to the knapsack approximation that can derive tighter bounds for specific values. So, but what's the upshot? What's the connection to zero-knowledge proofs? Well, we can get a polynomial commitment scheme either from groups of unknown order or from integer lattices. So we use this to first resolve a bug in the analysis of the original dark paper. So you kind of recover the dark polynomial commitment scheme with the original parameters. But I'll present this in a slightly more general way, right? Because the motivation was looking at dark, but there's like a more general result here. So we can use this to show soundness of folding schemes, also known as, a special case of folding schemes, also known as generalized bullet proofs, for this short homomorphism preimage relation. If the honest prover basically has an input to a homomorphism phi, such that phi of x is equal to t, and phi is a homomorphism from an integer vector of length n to the group, and it has this short. Doesn't just have any input. It has a short input. It's less than some bound b. We can think of the L2 norm for now. Then there's a soundness slack parameter which comes out of the short zippo lemma, and the size of the slackness parameter is 2 to the O of lambda log n plus log squared n. So the prover needs to use the prover is going to try to prove that it has this short preimage, and we won't actually be able to prove that it has a short preimage. It will have to prove that it has. This is due to the soundness slack. It ends up proving that it has something that's short, but a factor psi larger than the preimage it actually has. And we need additionally to use a deterministic commitment scheme that is binding to integer vectors of this larger norm, sigma times beta. Okay, and then you can just run basically bullet proofs on this modified homomorphism that takes x and outputs this commitment to it. So it needs to be a homomorphic commitment scheme, and this target value t. And the verifier is going to check that the final prover message is an integer of size bounded by beta times 2 to the lambda log n. Right? That's the protocol. And this ends up being an argument of knowledge for sort of an approximation of what the prover wants to show, which is that it knows some witness, x star, and some approximation factor a, such that this homomorphism evaluated on x star is equal to a times the target ct, right? So it's basically opening a times c instead of c, and it's showing that this the thing that it opens to evaluates to a times t, which you can think of basically as lifting this homomorphism to basically a homomorphism over a module over the rationals, and then it's showing a preimage of that in this larger module. So there's a slackness loss of the bound, and there's also slackness loss in the fact that you're opening a rational instead of opening an integer. So in a special case of polynomial commitments, we can just look at this homomorphism as basically a univariate polynomial evaluation. And in this case, the prover needs to start with something which is in 0p to the n. So using the L2 norm, our bound is basically square root of n times p. And we can interpret a rational opening here as just opening C to this polynomial in FP with coefficient vector x star A inverse mod P, right? And it turns out that if the commitment scheme is binding to vectors of norm at most xi times beta, then it's also binding to rational openings for any beta 1 and beta 2 if we can bound this x star less than beta 1 and a less than beta 2 such that beta 1 times beta 2 is equal to psi times beta. Okay, so it's binding to these sort of relaxed openings. And so we just run the protocol as is, and this gives us basically a polynomial commitment to univariate polynomials mod p. You can also do multilinear polynomials. I'm just giving the special case of univariate polynomials. So there's two concrete instantiations. In dark, we would set, the commitment scheme is G to the fx of Q, where fx is the univariate polynomial with coefficients vector x, and Q needs to be 2 times this larger bound, psi times beta, okay? And G is this random element of a group of unknown order. This random order assumption needs to hold in the group, and using log n proofs of exponentiation, you can actually make the verification of log n. This is a variation of the dark protocol that uses like it's based on bullet proofs, but you can still get logarithmic verification with some tweaks. And then the other instantiation is integer sys, and this again you just need to set Q to be sufficiently large. And the communication in the two cases are, well, logarithmic number of group elements for dark, and for integer sys, it will be a logarithmic number of integer SIS commitments, but each SIS commitment is lambda log n bits. Okay, so the overall proof size is O of k lambda log n times another log n, so O of k lambda log squared n. So prior work on bulletproofs PCS from lattices required using ring sys, and it required sampling challenges from exceptional sets which have only polynomial size. So this is at least to my knowledge, the first variation of bulletproofs for lattices that has exponential size challenges, which is important for when you do Fiat-Shamir. It's not clear that parallel repetition works well with Fiat-Shamir. So thanks.
Okay, sure, yeah. Hi, everyone. My name is Neil Fan. I'm a co-founder of SISIC. At SISIC, we do hardware acceleration of zero-knowledge proof. Like, there are many applications of ZKP in blockchain, such as like you can use ZKP to do a layer 2 scaling solution for Ethereum, and also you can add privacy features to the layer 1 blockchain. And also it can be used to bridge different blockchains. Despite these wonderful, wonderful applications, we still need some computing hardware to deliver the proof. Like in the proof generation of the ZKP is quite slow. And based on our profiling, like there are basically 3 components of the proving time. Like one big chunk of it, like which is around half of the proving effort is MSM, which is multi-scalar multiplication. And then around 25% is like NTT or like the soundcheck protocol. And there are some other fluffy parts such as witness generation. So here, like the MSM is our priority target. Yeah, so in this table, we summarize our effort of like using FPGA to accelerate the MSM part. We do our experiment from like 2 to the 20 to 2 to the 30. And yeah, so based on our experiment, we are faster than the current state of our implementations on a slightly larger FPGA. And we are the first one to run this like 2 to the 30, which is like 1 billion MSM like in less than 50 seconds on our FPGA card. And yeah, we finished this like in like 1 month, and this is just the first step in our final target, which is the ASIC. So in the ASIC, so that's the floor plan of our ASIC. Like there are several PEs on the ASIC. Like our projection is that we can finish this 2 to the 30 MSM in less than 3 seconds with a 16 PE at 300 megahertz. And if you enlarge one PE, like this MSM PE, you can see like the MSM EC point add and MSM point double. They are like 2 big chunk of the space. They take almost I guess 80% of the area, and there also is like this like PCIe agent which is like responsible to talking to the outside world. Okay. And our overall architecture is like to combine this like FPGA and ASIC. So we run this like common ZKP operations such as MSN and NTT on our ASIC. So we have a bunch of ALU clusters which are responsible to do the computation, and it's surrounded by like the PCIe, DDR, and SerDes, which is responsible to talk to the outside world. And we put on the project-specific operation, like weighted generation or MLE on the FPGA, since they are like frequently being updated. And these two components are like connected with each other using a high bandwidth SerDes channel. So combining the FPGA and ASIC, we can like deliver the best proving effort. Yeah, so what's next? Like we finished our prototype of FPGA of MSM, and we are like currently working on this NTT MLE and weighted generation, and we are very happy to like collaborate and integrate with current layer 1, layer 2 project. So please then let us know. Yeah, thank you.
The last one will be Merrick, and he will also show a demo on his own computer. Yeah.
Awesome. Hey, everyone. I'm Marek Olszewski. I'm one of the co-founders of Cello. And I wanted to talk a little bit about something that we've been working on for the last 2 and a bit years, and that's Plumo. It's a snark-based like client protocol for Cello. Cello is a fully EVM-compatible chain that we launched not too long ago. And this is joint work with these really amazing, esteemed collaborators. And so just as a quick refresher, if you want to build a light client protocol for a modern proof-of-stake network, you would most likely download and iterate through every header since the network launched and verify that 2/3 of the validators have signed off on each of those headers. While you're doing that, you'd probably also want to update the validator set if there's any validator set changes. And that lets you get to the last header, which lets you get to the last state root commitment, which then allows you to effectively verify any data that anyone sends you, even if it's from a non-trusted RPC node on the P2P network, using Merkle proofs. And so with Plumo, we initially wanted to build all of this using snark proofs, but not surprisingly, this was quite expensive. And so we made a number of optimizations to make it more efficient. Number one, we only allowed validator state changes to change once per day or once per epoch. This is effectively a 17,000 times reduction for us because you only have to check the last header of each day. We also used BLS 12377, the BLS 12377 curve for signatures, and then we use BLS signature aggregation to create a single multisig of all of these signatures. All of these things meant that it became actually feasible for us to build snark proofs that prove our proof of stake in our light client protocol. And so, after we had the design for this, it took quite a lot of time, over 2 years of development, a lot of time focused on optimizations to make the proving time fast or still slow but manageable, and obviously a lot of work to audit this to make it a fully production-ready system. We ended up creating really a massive circuit with 2 to the 27 constraints on BW6, which is a very big curve. The validators sign on BLS 12377, and we use 1 layer of recursion. And then we were done. We got it all developed, audited. We were so excited, and then we realized we needed over 2 years of CPU time to actually run the trusted setup. And we're like, oh crap, that's going to take a while. And so instead of waiting all of that time, we actually worked on an optimistic pipelined powers of tau ceremony, which allowed us to effectively parallelize this. And I believe there are other projects now that are using this exact ceremony for their own launches as well. And after that, didn't quite take 2 years. Still took a few months. We're super excited. We launched Plumo earlier this year. We now have folks in the community that are generating these snark proofs daily after each epoch change. And what gets me really excited is we released a WASM library that lets you verify these proofs and effectively sync with the P2P network, and then verify arbitrary data in the chain, in the EVM chain, not just from mobile applications, but even from web apps. And I think that's definitely a first. And so I'm so excited by this that I want to risk angering the demo gods and demoing this for you. So I'm going to reload this so you know it's a live demo. This is on the university Wi-Fi here, which is a little slow right now because of everyone here. So this is a web wallet that's commonly used in the Celo ecosystem. It's celowallet.app. And we updated it to verify all of your balances using Plumo and using Merkle proofs for each token that you have. So I'm going to press enter, and this usually takes about 2 seconds. It might be a little longer here on the university Wi-Fi. There we go. We're done. So in this time, it downloaded 4 Plumo proofs that effectively let you fast forward by about half a year on the network. It verified all of those Plumo proofs in WASM in this web app, and then it downloaded 4 Merkle proofs and verified each of those 4 Merkle proofs. That's how we could have gone longer, but would have required going more than 2 to the 27 constraints, and that would have meant proving time was a lot longer. Proving time already takes about an hour on the beefiest machine that Google offers. I think that's a 256 core machine, which is fine because we only have to do this once per day, but you know that's still big. And actually the biggest limitation is not CPU, but memory. That machine has terabytes of memory, but it's still going one level up would have meant that we would have ran out of memory. I'm also working on, this is just yesterday, I thought I'd try to build this in time for today, a fun little forever bulletin board where it's a web app that uses Plumo that can be hosted on IPFS and effectively would allow you to add notes and have people view those notes without having to go through a trusted RPC node. So it's pretty cool. I'm looking forward to open sourcing this for everyone to see and play around with, and hopefully we can have some forever notes floating around. And that's it. Yeah, thanks so much for your time. And maybe one super quick PSA, if you enjoyed this talk, we're having a little event on Wednesday in the Celo office. I'm calling it the Celo Connect Salon. So definitely come by. It's you can RSVP at celoconnect.com.
Okay, thanks a lot, and thanks a lot for all these great contributed talks. And also, hopefully, Merrick's talk can also show that with this ZK proof approach actually has many benefits, including enabling trustless, trust minimized live clients, and also the ZK bridge approach that we mentioned earlier. And also, Celo is actually part of the ZK collective. Right, yes, and together with many others. So that's why I said, if you are interested, we would love to have you join the ZK Collective. And so now we're going to have a break for lunch. And so we have some lunch boxes, and also there's a pizza coming as well. And we have a lot of talks going in the afternoon, so we'll restart at 1 p.m. On time. Right. Okay, thank you.